So that's why we think there must be a higher limitation for vegetation growth due to water limitation. So how do we test that? That is the problem, right? Because there is no like a single index. I can say, that index is bigger. That means vegetation is more water constrained. There's no index like that. So how do we do that? So we basically borrow method from this paper, right? So we basically using a simple correlation between vegetation growth data and the water availability data. For vegetation growth, we can use multiple index. We can commonly use NDVI, normalized vegetation index, or we can use some newer product like vegetation optical depth, VOD, or like a GPP product from a satellite, or SAFE product. Maybe some of you heard of that. But so it's really just a satellite product to indicate vegetation productivity. And then we can use vegetation water availability data. One we use is SPI. People use as a drought index, but it's actually more commonly you can use that as a vegetation water availability index. Higher number means more water, lower number means less water. So same as the PDSI. So what we did is we make a correlation between these two, right? We look at whether you have a positive correlation or negative correlation. So if we have a positive correlation, we consider this region is a water deficit region. Why we say that is if you have a positive correlation means you add more water, plant grow better. If you have less water, plant grow less. So that's a positive correlation, right? So if you have that, we talk about that means in that region, that's a water deficit region. But if you have a negative correlation, that means if you add water, plant grow less, right? So that means it's not water limited, it's a water surplus region. So that means it's energy limited. So if you think about like a northern region, boreal forest, for example, they are the energy limited system. If you have more rainfall, more water given to them, they won't grow better, they grow worse. So that is a water surplus region. So first thing we do is we classify the global vegetation map, every grid cell. We classify them into water deficit region and also water surplus region. And then we look at the trend over the years, how many grid cells will become from water surplus to water deficit. That's what we are looking at. So, but first we test whether this correlation concept makes sense. We make the correlation and then we look at how this correlation distribution is. So you can see for this map, all the kind of dark color here, they are positive correlation. Right? Most of them are concentrated in the lower latitude. And then when you look at the bluish color, so that's all negative correlation, right? So they are all located in the higher altitude. So, that's already tell us, the correlation actually makes sense. So the lower latitude, that's the kind of a dry land, right? So they have a positive correlation. And for the higher latitude, you have a negative correlation, right? So we can also look at this, right? So they are the aridity classification of different regions, arid region and humid region. So the arid region has a positive correlation, humid region has a negative correlation, right? So this is just a first test, say whether this correlation idea makes sense. So it does make sense. Really, the more important thing is we are looking at how these correlations are changing. So this is really this map has a two-dimensional information. So you have basically whether they are positive correlation or negative correlation. And then also whether the correlation are increasing or decreasing. There are two-dimensional information. So you can see there are places like a pink color. They are positive correlation, but also the positive correlation becomes stronger. So that means they are water limited condition, and the water limitation become more severe over the years, over the last 30 years. And but there are also regions, they are water surplus region. and the surplus region become less severe over the years. When we add up every single cell, when we put them together, so that was a general trend over the last 30 years, from 1982 to 2015. So what we saw is the water deficit region, the area become bigger and bigger. And for water surplus region, the area become less and less, right? So that's actually give us the most direct evidence to show, okay, as a global scale, or at least not the hemisphere, so the water surplus region become less, water deficit region become more. That means vegetation growth does become more and more water limited, right? So that is one of the most direct evidence we have. So remember this one we use NDVI, right? So we want to test whether the results is robust. So for Nature type of journal, you have to show your results is robust. You can't just use one index, one product. You have to use multiple products. So then we use different NDVI from different sensor, but also we look at different averaging time and different moving window. But also here I didn't show we use VOD data, we use SAFE data. They all showing very similar pattern really. So here just the same information, but really just telling us regardless what product you use, we're actually showing the same pattern. The water deficit region become bigger, the water surplus region become smaller. And then that's one evidence we have. The other evidence we did is we actually average all the grid cells for their correlation, right? So it doesn't matter negative, positive, we average them across the whole globe. We add up all the grid cells and we looking at the average, how the average has been changing. And what we found here is regardless we use SPI or PDSI. What we found is the correlation has been, the average of the correlation of the whole globe has been increasing, right? So because remember we talk about higher number means, that is more water constraint, right? So that also gave us evidence to show that at a global scale, water limitation become more and more severe. So that's another evidence we provided about the increasing water constraint. So last evidence we have is actually the response time, right? What I mean response time, sorry, there's another evidence, but this is the second last evidence. So is the response time. So response time here means, for example, if I have a drought condition, right, the plant won't grow as well, but they could happen in 1 day, but it could happen in 10 days, or could happen in 1 month. Right? So that's what I mean response time. So what we show here is vegetation response time. We look at water deficit region and water surplus region separately. So on the top is the water deficit region. So what we saw is the percentage of a region their response time decrease is much bigger region than the time increase. So what tell us is on average, so the response time in responding to water shortage become shorter and shorter, right? So in the past, maybe 1 month, if you have a drought event, plants start, didn't grow well. Right now, maybe you have a half month, right? So the response time become shorter and shorter. That's for water deficit region. So for water surplus region, it's actually very similar. So the response time also becomes shorter. So remember for surplus region, we talk about if we have a short drought condition happen, it's actually benefiting the plants. It's actually a good thing. But the period of benefiting could be 1 month, could be like 10 days. What we show here is as time goes by, the benefiting period becomes shorter and shorter. In the past, maybe 1 month is actually benefiting, but right now it's maybe like 1 week, right? So that's also tell us, the water scarcity for vegetation growth become worse based on response time. Their response time becomes shorter and shorter. That's a third evidence we have. Any questions for how we got this? Okay, so the last evidence we did is, so this one, we just picking the, you don't worry about this, so we just talking about, we detrend the vegetation using linear method or non-linear method. They give us similar results, don't worry about that. So, but really the idea here is, instead of using correlation, that's an independent method, we don't use correlation anymore. But we only look at based on SPI, based on PDSI for that grid cell, whether that is a drought year or not, a drought month or not. And if that's a drought month, we'll pick up their NDVI value odd. And if not drought month, we don't worry. And then we do that across the whole globe. And then we're looking, so basically what we are looking, if we're looking at only drought condition, how vegetation has been changing. So basically what we saw is if we only look at the drought condition over the last 30 years, so the vegetation index has been declining regardless what you use, SPI or PDSI, right? Regardless is like a linear or non-linear trend. So really the key message here, remember this is totally independent. We don't use correlation. We just picking up the NDVI value when they are under drought condition. And what we show here is over the years, if we under the drought condition, plant growth become less and less well, right? So that's give us the last evidence. So basically we're using 4 pieces of evidence to show over the last 30 years also, as a global scale, vegetation growth become more and more water limited, right? So any questions? Okay. And so far when we talk about water availability, we really talk about rainfall amount, right? We just talk about how much total water we have. So we rarely talk about the rainfall variability, like how rainfall got delivered. But for this newer paper and part of it, we are actually using the satellite information to show actually rainfall amount and rainfall variability both are very important. So this is based on statistical modeling. So, but the idea is basically what we saw here. If you compare rainfall variability impact and the rainfall total amount, so they actually almost comparable in terms of the region they affected. Based on the numbers, 23% is basically like a positive affected, and 19% of area is negative impacted. So it's regardless the number, but really just talking about the magnitude. So the rainfall variability impact is on the same magnitude as the rainfall total amount. So I guess the idea is in the future, when we think about the rainfall impact on vegetation, we shouldn't just focus on the total amount itself. I have to think about the variability. Variability could play a role as well. So I guess this one I won't elaborate too much, but the idea is, if you have a blue dot, that means, they are positive response. Like a red dot, red color basically means negative response. So because depends on whether you are dry land or like you are non-dry land, their response could be positive or negative. But what we are arguing is really the area is actually quite comparable. So not the direction of the response. Any questions for this? So far what we talk about is essentially drought condition, right? How drought impact the vegetation. So the next part I'm going to talk about is just one paper, right? So talk about the flooding impact, right? So this one is the one when I doing the tutorial, remember I mentioned this paper, right? So it's leading by a collaborator from IU, from another campus, IU Bloomington. So for this one, we really talk about the impact of vegetation on flooding events. Right? How that, to me, the key message is flooding will happen more frequently, but vegetation can help us. They can mitigate the impact, make the impact smaller, right? That's the take-home message for this study. So, and I will give you some rationale and also some how do we exactly did that. This is just based on modeling, based on model results, right? It's not based on satellite or any observations. So, I guess we know flooding frequency has been changing just like a drought, right? So because of the precipitation pattern change. And also we know even right now, right? So the flooding events has been negatively impact us in many different ways, right? So, but also most of the time people always assume if you have a higher rainfall events, you must have a higher flooding, right? So that's a kind of common assumption, right? So, but in reality, right? For example, in this paper, so basically what people show here is, if you have a higher rainfall events, this across whole Europe. So when you have a higher rainfall events, doesn't always you have a flooding. Sometimes actually lower flooding, right? Some places sure you have a higher flooding events, some have a lower flooding events, right? So that's basically tell us why that is the case. So that's exactly we try to answer, right? We try to, our hypothesis basically is actually vegetation play a very important role, mitigate the flooding events. Depends on how do they do, is actually will have a flooding or not. So, for this work, we also identify one of the gap in the past work when people doing the flooding events. So they actually, most of the time, they do as a seasonal time scale or even annual time scale, right? So, but this is, just because if you do long-term trend, that's the only things like maybe available to you. But the thing is, when we think about the flooding, right, so a lot of time that is event-based, right? You have one rainfall events, you may have a flooding events after that rainfall events, right? So ideally, we should actually deal with the flooding as an event base. So, but it's not always available, especially when you think about the global scale, right? So because that will be a very large data set. So that's why, when we think about how climate change will impact the flooding as an event scale, is still not widely reported. So that's why we did this study, try to answer that question. So again, this is a model-based study, right? So that's why, this work was originally submitted to Nature Geoscience and it actually was reviewed there. But yeah, I guess the reviewer has a point, that's all the results are from model. How do we know that is the right results? It's a valid results, valid criticism, right? But sometimes, that's sometimes is every study has limitations. So for this particular study, we did use like a model ensemble, but we only use one model. So this is a CESM is basically community land model, right? You may heard of this. It's one of the large model people use, developed in the US and widely used. It's one of the member of CMIP 6, right? So we talked about CMIP 6 in the past. And we use different future scenarios, SSP 3 to 7, and so that has future predictions. We'll get data from every grid cell globally and as an event base. So, like we talked about, that's very computational intensive. So we have to, like a single computer can't be able to do that. So we basically use so our university has a supercomputer called a Big Red 2. So that is has a very high computing power to be able to do that. So what we did is, we found historical data and we pick up all the 95th percentile of the rainfall events, and also we look at their corresponding runoff. We'll pick up all the data from every single grid cells from global scale, and also we'll then calculate the runoff ratio. Runoff ratio means the ratio between runoff divided by precipitation. So some places they may have an increased runoff ratio, right? So some places they have a decreased runoff ratio, right? So our hypothesis is really related to the previous soil condition. So if you have a pretty wet previous soil moisture condition, right, very likely if you have a big rainfall events, your runoff ratio will increase. If you have a very dry soil condition, and if you have rainfall events, the runoff ratio may not increase, maybe actually decrease. So basically, we just pick up all the data from soil moisture and also the rainfall data and the runoff data from like every single grid cell, and look for all 30 models, make an average, make an example of all the models, and also look at different scenarios. So that's how do we did this research. So here is a kind of a quick results. So this is a comparison of projected rainfall events, projected rainfall in the future compared to like a reference period. So the key message here is what we saw here is in the future will be much wetter globally when we think about the end of the century. So most of the places is higher rainfall events, right? So that is a projection for rainfall events. And then we can looking at the runoff ratio. So remember we talked about runoff ratio is actually quite surprising. We actually found many places they have a reduction in runoff ratio. But even you have a higher rainfall events in the future, the runoff ratio is actually lower. But there are places has a higher, but many places they have actually lower runoff ratio, right? So why is that? Like I mentioned, our hypothesis is because of vegetation. If you have a higher vegetation cover or greener vegetation, right? So they can take up a lot of soil moisture, make the soil moisture less. That actually can reduce the runoff ratio. So what we did is we did look up the previous surface soil water conditions for every grid cell. So we can say actually this map is very similar to this map. You can, based on the comparison of these two, the soil moisture, previous soil moisture condition always matching the runoff ratio. You can actually look at based on the relationship between soil moisture and runoff ratio. They are scattered, but almost like a linear relationship there. So that's basically tell us soil moisture play a very important role. So we can also use a random forest type of machine learning technique to look at the major contributor for runoff ratio decrease or increase. So you can see the major players for runoff ratio decrease. One is transpiration, canopy evaporation, and the ground evaporation. So they are the major players. Right? So the same for runoff increase is also transpiration, evaporation, and the ground evaporation. So basically, to put this all together, what we think happen is soil moisture condition, the previous soil moisture condition play a very important role for flooding events. If you have a higher rainfall events, it really depends on whether you have a higher or lower previous soil condition. If you have a lower soil moisture condition, you tend to have probably flooding events. You may not have a flooding events, but if you have a higher previous soil moisture condition, you tend to have a flooding events. So but why that happens? Because of vegetation. So because in the future, when we do the projection, we are talking about in the next 50, 80 years later, right? The vegetation become greener, become bigger, right? So they will actually mitigate the water loss through evaporation, transpiration, right? And the soil moisture change. So because they moderate the water cycle. So really the take-home message here is vegetation play a very important role in terms of mitigate the changes in flooding in the future. So just a quick summary for what we talk about the flooding part. So what we show here is a runoff generation from extreme rainfall is complex, right? So it actually depends on the rainfall itself, but also depends on the condition, the previous condition of the soil condition. So if you have a drier soil, means you may not have actually flooding events. If a wetter soil, you very likely have a flooding events after extreme rainfall events. So, and also we talk about, even with increase in extreme rainfall in the future, actually majority of the place we saw is actually has a reduction of runoff ratio. Right? It's runoff ratio, not runoff, right? So remember. So, and the mechanism for that we talk about is because of vegetation, right? Because we have a vegetation gradient in the future, and that vegetation gradient will actually decrease the soil water content. So because they decrease soil water content, that actually will prevent flooding events after heavy rainfall events. So really here just implications, right? So if we know vegetation play a very important role for mitigate the flooding risk, that means when we think about the city planning, right? You have to think about make sure you plant plenty of trees, that can help us with flooding condition, right? Even in the future, we know there are extreme rainfall events. If you have a lot of vegetation there, that means very likely the chance of flooding events will be reduced significantly. So to summary both part, right? So for the drought part and the flooding part, really what we saw here is based on the flux tower synthesis work, what we saw here is the drought timing play a very important role for ecosystem carbon sequestration. If you have a drought happen in the late growing season, that's very bad. But if you have a drought happen early growing season, it's not too bad. And then I talk about we develop a multi-sensor based drought index that actually can be effectively capture drought almost as good as USDM, the widely used one in the US. But this one is a drought index, is a continuous value, is remote sensing based. It can be applied to other place, other continent. And based on the correlation between vegetation index and water index, what we show here is in the past 30 years, we think vegetation growth has become more and more water limited, right? So one of the evidence, another evidence is we saw the response time to drought is much shorter now, and also if we pick up only drought condition and look at what plant growth is during that period, we can say over the years, if you are doing the same type of drought condition, the vegetation growth has become less. And then last, when we talk about vegetation gradient, basically we are talking about, in the future, sure, there likely has more extreme rainfall events, but that doesn't necessarily mean you have to have more flooding, because vegetation become greener and that they can actually mitigate the flooding events. It could be actually have a lower runoff ratio in the future. So, but again, this one is purely based on the model projections, right? So we don't really have a way right now to validate in the real world yet. So I think that's all. I guess just again acknowledging our funding source from different federal agencies in the U.S., but also for my group members for their contribution for the work I taught here. So hopefully, I don't talk too fast, and you get the key message, at least more. For the method, some of them is tedious, may not be as easy as you think. But if you have a question, feel free to ask me. but hopefully you get the general picture about the general results and also the implications. Yeah, thank you guys. Any questions, comments? So hopefully that's because everything is clear enough, not because everything is not. It's just yeah. Yeah, that's a good question. I mean, there's no way to validate future projection, right? So the only thing you can do is you you can use the, for example, if you find a relationship you think that will happen in the future, right? So you can only validate the part currently using the data to validate that relationship. If for example, if your model output, for example, for this one, what we did validate, what we validate is, we can't validate the future part, but we can validate like in the current data, we have a runoff ratio, we have a soil moisture. We can do this relationship for the current setting. So if we can match the current setting and the model results, we have to assume the relationship will stay the same in the future. So I guess, yeah, that's the most commonly people does, is because there's no future observation. We have to rely on, but of course the caveat for that is you does assume the relationship stays the same right now and in the future. But in the future, sometimes the relationship may not hold. That could happen, but that's the best thing we can do. Just using the current observation to validate your model output. And then if the model output captures the current observation, you can say, then I can do the prediction now. Yeah, thanks. Sure. Any other questions, comments? Yeah. So what kind of vegetation? Yes. So, yeah, so the question is, yeah, I guess what kind of vegetation responsible for this? But remember, this is, let me see whether I have the spatial scale. So this is a global modeling study, right? So I don't have that, but this is a 0.5 degrees C, like a 50 kilometer by 50 kilometer, right? So in a way, we don't really care or don't know what vegetation is. It's just in general, there are vegetation there. But of course, in reality, most likely we're talking about trees, right? So that's the major player in this. But yeah, for any of the global study, most of the time, the best people can do maybe 0.1 degree. That's still 10 kilometer by 10 kilometer. So that's already very high resolution for global scale study. But even that, you can't really tell too much about the vegetation type. So yeah, for like a regional local study, for modeling study, you can easily do that. But globally, very rare people were able to do that. Yeah. Yes, that's a good question. Any other questions, comments? Okay. Yeah, I guess that's lunchtime now. Then. So yeah, again, yeah, if you have questions, yeah, feel free to come to me separately. If you have a question about certain procedures or just a general questions, I'm happy to answer it. All right, thank you guys. some satellite information you can find. So the high resolution. Yeah, I mean, depends on what the product you have. Because there's a good one is the centimeter. Yeah, it depends on what lens size is 40 days. But there are some daily products. There are like molded is 60 days. And lens size is actually every day. And also the newer one, like centimeter. Yeah, there should be daily. Should be daily. Or at least maybe 2 days. You don't have that. Because sometimes you can't validate everything. You just look for days. You have data. And maybe over 10 years, you have like at least 1 month like data data point you have. Then you can just validate that 1 month. You don't have to 10 years every time you validate, right? So I mean, to me, really the key point is you validate what you have, right? So try to get as much as observation as you can, because the more validation you have, people trust your results. So like a satellite is one thing for in the area, but also maybe soil moisture. If you have a sensing based soil moisture like SMAP, and that's why you can compare with a model, not like numerically like it has to be exactly the same, but the spatial pattern. If the spatial pattern is matching, because SMAP may not be totally correct for your region, but if the spatial pattern soil moisture matching your model, that's already very good. So give you confidence at least you capture spatial. Exactly. Yeah. Yeah, because sometimes you don't know the number is correct number, right? So, but at least you have to have it. So, yeah, I guess really the point. Yeah, just try to think about whatever you can find, right? So, and then validate. Yeah, that's what we do. Sometimes, I do. Maybe tomorrow, I will talk about the form and view. Nobody measures it, right? So you have to just find the record yourself and try to use whatever you have. driver will pick me up before 3. Okay. Good? Okay. All right. Good afternoon, everyone. Well, I like the attitude. That's good. Yeah. So it's me again. Yeah, I never actually gave a talk such intense pace. Yeah, it's actually a new experience for me. So we will, for this 1.5 hour-ish, we will do a tutorial, right? So basically, doing the meta-analysis like the one I talk about in the morning. So before I start, any questions? So everybody has a computer? Okay. Yeah, because we'll use a computer for this. So yeah, I guess the topic we are going to try is meta-analysis. So we already kind of touched on this, right? So what is a meta-analysis? So meta-analysis is a statistical technique, right? So it's synthesize data from multiple studies and try to look for common patterns. So that's the kind of essential aspect of a meta-analysis. So it was started in medical field, right? So because if you have a new medicine, you want to test whether it's effective or not. So sometimes, the treatment effect may be subtle, may be small, right? You need a very large population to do that, and there are a lot of variations. So people develop this technique and try to capture the treatment effect more effectively. And then later on, there are many research field has been adopting this type of research, try to look at the treatment effect. So really the key thing you want to use for meta-analysis is you try to look at whatever the treatment you are looking, like either drought or flooding or maybe a new crop species, how they are changing the outcome you are hoping for, right? So that is in science for meta-analysis. So again, meta-analysis doesn't really generate data on its own, right? So you actually go to literature to digitize the papers, research papers. You generate data that way. So you don't really collect data from the field or doing remote sensing. So that's kind of the simple way to think about the remote meta-analysis. So why meta-analysis is useful, right? So because it's provide way quantitatively synthesized data, give you the kind of quantitative information. And because you use a very large sample size, right? So a lot of time when you do field research, for agricultural research, for example, you only have a couple of fields, and you have a limited size, sample size, either like a couple years or sometimes even one growing season, right? So for meta-analysis, you try to synthesize studies from all over the place. You could have very different soil texture, different temperature, different crop type. You can actually put them all together. So increase the kind of the power of your conclusion, because it is based on a very large data set, give you a general trend. And also, a lot of time for individual studies, there are different results. And by doing meta-analysis, hopefully you should be able to find a common trend and try to reconcile why these two studies are different. You can give a reason why it's different. So that's why meta-analysis is quite powerful. It's quite useful. So really the key thing, the most time-consuming part, I would say, is kind of digitizing the literature data, right? Because you have to go to every paper, and a lot of time you digitize the data from the figures in the paper. You take them out. There are many software you can use to digitize that. But if you have data already in table format, that's actually much easier. Right? You can just read out the data. So here I just give you an example how meta meta-analysis is more powerful compared to regular, for example, review paper, right? So if you working on review paper on certain topic, maybe whether flooding will, or I mean whether whatever, I guess, topic, you have to have a treatment, right? So the treatment could be drought, could be flooding, could be anything, heat wave, right? If you want to say whether, for example, heat wave will change this certain crop yield, you want to test that. So, traditional way, when you do a review, you will go to different studies, right? So you will see, okay, this study has a certain data. They get a conclusion, maybe impact crop yield or maybe not. And then you go to a second study, you also get the conclusion, impact or not, right? So, then you go to maybe number of studies and try to say, okay, overall, how many actually are finding the drought or heat wave impact the crop yield for that species, and how many are not. Really, you're just kind of counting the vote, right? Either this is yes or this is no. You just simply count them. So that is, I guess, the most common way, most traditional way you try to synthesize literature data, right? So that is good. That is one way to do it. But the downside is you're really just kind of using the secondary information, right? People already draw a conclusion. You just count how many the conclusion for 1, 2, 3, and you make your own conclusion. For meta-analysis, you really don't care about the conclusion people made in their own paper. What you do is you really just collect data from each study, and then you combine the data. You don't combine the conclusion, right? So you actually rely, your own conclusion is rely on the combination of all the data, right? So that is a difference between kind of a traditional way to deal with data synthesis review paper compared to meta-analysis, right? So that's make sure you understand the difference, right? So there are many different software can help you digitize the data, but also synthesize the data, analyze the data. So today we'll basically try to let you have a little bit taste for that process. So why is very useful. Also, you can actually reflect it in the real outcome, right? So that's my Google profile. That's all the top cited paper I wrote, right? So you can see actually the one in the box. That's one all like a data synthesis paper. So you can see that's more than half, right? Really, I can say majority of the paper highly cited is actually through the data synthesis. So in a way, it's not surprising because you are helping people to synthesize that field. You already help them to make conclusions, so they don't have to read 100 papers themselves. You already gave them the information from that 100 paper, right? So it's actually that's why it's very, very powerful. So that's the paper I talked about earlier today, but there are other data synthesis we did from my group over the recent years. So, but just give you the kind of a practical benefits. Using that maybe will help you write impactful, like highly cited papers. Right? So that's but the difficulty for meta-analysis really is you have to find the right topic. Because if you have a brilliant idea, right, you want to answer a question, and then when you search the literature, there are only 2 papers there, then you can't really do it, right? So, or if you have a topic so broad, when you search for papers, you find maybe 10,000, 100,000, then that's almost impossible to, digest all of them, right? So you have to be able to find a question that is kind of broad enough to be useful to many people, but also not broad enough. You have just too many paper, you can't even handle that. So that part does require your kind of intellectual judgment, right? You have to read things, think about things yourself. What is actually the most pressing question I should ask, and do some preliminary searching, and like just look how many papers in that topic already, and then decide whether it's worthwhile I can do a meta-analysis, right? So that's something you have to decide. So when we think about the meta-analysis, really there are two important things you want to do after you collect data. That is important, it's tedious, but that's not part of analysis yet. So the analysis one, we basically try to calculate effect size. So what is the effect size? Really just you try to look at the difference between your treatment and your control. So for meta-analysis, because again, it's come from the medical field, right? So in a way, you have to have whatever the medicine as a treatment, and then you have a control group. So you want to say, when you compare this one, whether they are different or not. If they are different, means, oh, this medicine works, right? So that's the essential idea for meta-analysis. So the same idea for other field, really you try to say whether the treatment you are looking, whether, for example, if you want to say whether the flooding will increase, whether extreme rainfall will increase flooding in certain climate. You're just looking for like a data from that climate condition, looking for extreme rainfall events, looking for like a runoff, like data, and try to like have with rainfall events, without rainfall events, and looking at the treatment effect. So you have to be able to identify one treatment, one control, and then you make the comparison. But how exactly you make comparison, that is the effect size, right? So one type of way to quantify effect size is called the response ratio, or log R. So really you just take a ratio between these two and then take a log, right? So mathematically is equivalent to difference between log of these two values, right? So x2 basically is kind of the treatment value, right? So whatever the treatment you are looking at, and x1 will be the control, right? So that is your response ratio. So every single study, you calculate a response ratio, and then you synthesize all of them. So another way is called HD. So that's another way to calculate effect size. You can see really the major difference between these two is HD does try to incorporate information of the variability, standard deviation. And this one is just a correction for if you have a small sample size, there is a certain way you can correct for that. But really, you're thinking about the treatment difference and then standardized by the standard deviation of your study. So this one is less commonly used because many studies don't have the standard deviation reported. And this one is, I would say, the overwhelmingly more commonly used. But I would say maybe 60% using this, 20-30% using this, right? So, when you read the meta-analysis paper, that's kind of the divide. So really, for us, maybe for exercise we try to do today, we will just use this response ratio. So that's one thing. After you digitize the data, after you get your raw data, the first thing you do is try to calculate effect size. Then really the last step for meta-analysis is you calculate the confidence interval, right? The one I talked about earlier, right? So that's one, yes. Okay. So control basically is whatever you consider as a standard condition, and then treatment be some kind of either heat wave. For example, if you want to look at the drought impact on agricultural yield, like the one I talked about earlier, so the control will be no drought, like a normal condition. So the treatment will be drought condition, right? And then if you look at the yield, right, you really just look at the yield under normal condition, under drought condition, and then you take the ratio. So that will be the response ratio. You take R log of that ratio. That will be your effect size. So yeah, really the control and the treatment, it depends on what you try to study, right? So if you want to say, for example, whether warming will increase compound effect. I mean, it's hard to do control experiment. You have to rely on control experiment. For example, if I say, if I plant certain trees in this watershed, whether that will reduce the runoff, right? So that if that's your you are thinking about your treatment, so the planting the tree will be your treatment. Then you should find another similar watershed without planting the tree, right? So that's your control. And then if you're looking at the basically runoff value, you can just measure the runoff value in each of them, and then take a ratio. That's your effect size. So yeah, really, whatever the impact you want to look at, that's your treatment. Consider that way. Yeah. Sure. So, yeah, that's good. That's good. So after you get effect size, really the most important part is try to calculate this thing, the bars, right? So this one, like I mentioned, is a 95% confidence interval, right? So typically, that's statistically that is the range of your treatment effect, right? So if this one is overlap with 0, that means there's no change. The treatment and the control are the same, right? If this is like this, there's no change. So that means your control and your treatment is the same. And if you think about the drought impact on yield, means okay, drought didn't really change yield, right? So for this particular case, that's a paper we are going to use data from. We're actually looking at the cover crop impact on agriculture yield. Right? So whether if you use cover crop, whether that's increase or decrease or doesn't change your yield. That's our question. So here, basically, if you have things like that, that means cover crop really didn't change yield. And if you have things like this, that means cover crop increase yield. And if you have things like this, that means cover crop decrease yields because they are on the negative side, right? So that's basically the end product you try to get. So before I move on, any other questions? So if I try to understand the impact of a cover crop on yield, what is the treatment, what is the control right now? So I will have one field with cover crop, one field without cover crop. Which is control? So always the one without, the one without cover crop should be control, right? So that will be our reference value. And then the one with cover crop should be our treatment, because here cover crop is your treatment, right? So same thing if I try to look at, for example, simple question, right? If I want to say certain fertilizer works for the crop yield, right? So I have two fields, one will be adding the fertilizer, one will be not adding the fertilizer. Which one is the treatment? Crop yield, yes. So I guess in terms of one adding fertilizer, one don't add fertilizer, which one is the treatment, which one is the control? So the one adding fertilizer, that's your treatment, right? So the one without the fertilizer, that's your control, because you want to compare these two, right? So just make sure you understand that part. Any questions before we move on? So, for example, if I try to study, for example, how rainfall variability will change crop yield, if that is my question, right? So if I look, then I need to look for studies that actually change rainfall pattern, right? And if I have two field or two plots, one actually people change rainfall arrangement. One is not. It's just a normal rainfall. Which one is the treatment? The one changed, right? So the one normal condition, that's always your control. And then you take the ratio between these two to get your response ratio. And then after you get your response ratio, you actually calculate this. How do we get this, right? So because this one is not from a single study, this one depends on whatever you study. Could be from 10 study, 20 study, 100 study, maybe even 1,000 study, right? So that is actually a synthesis part. So, but each one, for each individual study, they only give you one response ratio. So what you do here, confidence interval, you really just synthesize all of them, getting the final product. This is the final product, right? So then we can, think about have a try, right? So there are different software can help you doing meta-analysis, right? There are a language, like a package you can do that. But I think for this tutorial, we'll use one easy to use. That is like Excel. Is you can search MetWin and look for this website and try to look for this software. There is a download button here. So they have both PC version and Mac version, right? You can download and then install on your computer, and then we'll start from here. So yeah, try to find this software first, and then we'll give you a data set, and then you can play with the data set and try to see how can you make things happen. So yeah, first thing, try to look for this software and try to install this to your computer. It's a free software. It's open access software. Anybody can download, can use. Yeah, if you don't have a computer, try to pair up with someone who has it. At least you have a experience, just running the software. So yeah, that's a web link. Or if you Google MetWin, you should be able to find it too. So get it? Good. Installed? Okay, good. Everybody is good so far? Okay. So this one is one of the commonly used one. Yeah, if you start with meta-analysis, you can start from this this one. You can use this one for final publication too. So for interval data set, because it's good to have a standard you can compare your results with, right? So let's just use published papers. So that's the most recent ones from my group. Like I mentioned, that's one we actually looking at the cover crop impact on crop yield, right? So this one published last year. So try to Google this one, and I'm asking to do this one because we did publish the data too. When you go to the website, you should be able to find the supplementary material. That is whether you did it correctly or not, right? So yeah, just try to Google this one, and you should be able to find the data file. There will be a supplementary file associated with this paper. You can download that Excel file, and we'll use that data as our exercise. Yeah, so as a good example, like this paper published last year, right? I think it's already been cited for almost 30 times. So, it's really just tell you if you're actually doing some like a good synthesis, is really good for other people to use your work. Yeah, you can use Google Scholar to search this, and there should be an Excel data file associated with this publication. Do you guys have a issue to access the data set? You found it? No? Found it? Download the data already? Okay. So yeah, if you find the paper, you need to scroll down all the way to the bottom. I think will be a supplementary table, right? So that is the one we provide all the data. So we try to, when we publish paper, we try to make them open access. Everybody can check the results, can use the data. So there is a data set basically associated with this paper. That one already digitized everything, right? Everything is already done for you. It's already there. We basically just play with that data, and that data table should be part of the file. If you go, so you didn't find the Excel. Sorry. Yeah, let me go closer. So you said there is. Oh. Okay.
There is one problem which is related, seems like that it is related to this problem. That is something we call it as bibliometric data.
Okay.
So in bibliometric data, what we do is we take all the publications.
Sure.
From on a specific research paper.
Yeah.
And then we try to find out what were the important keywords. And what is the important findings.
Yeah.
How the themes of that particular field evolves over time.
Yeah, the evolution. I know what you are talking about.
Yes.
That is based on the text, right? So you actually digitize all the text, and you make
We
yeah.
process the text and then. So is that problem has to do something with this one, or we are only extracting the data and we are performing the qualitative analysis, quantitative analysis?
So for that one, I think it's less used really, because that one is based on, analysis frequency of the data. Depends on algorithm, right? They may do things good, maybe not, right? So there's some subjectivity there. So this one is really just building on the actual data. You synthesize actual data, so it's more objective. So that's why this one is tend to be, I guess, more commonly used.
Different kind of results than that thing.
Yeah, I think so. So because that one is, in a way, it's not quantitative information, it's more qualitative information. So it's like which field is a hot topic, and who did what, was evolution, right?
One kind of that analysis. That's why I thought, because I haven't heard about this one.
Okay, okay. Yeah, I mean they are related, but totally different techniques. Yeah, yeah. But I know what you're talking about. Yeah, 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 yeah. So I just try to check how. So you guys find the data? You did. Yeah. I think the university should have. Yeah. You should be able to download the data. I just wait a few minutes. You want to download the data. Any questions for the data? Everybody downloads the data? Okay. So yeah, I guess I can show you. Let's see whether I can. So if you open up the software, it's something like this, right? So I guess one of the downside for this software is not data input friendly, right? You can't even copy paste from other place to this. You have to load the data, right? So that's why you have to rely on the Excel you have, but you need to make some modification. First of all, this one, when you load the data, it doesn't load Excel data. It only load like a CSV file, right? You have to convert. So for example, that will be the data set you guys got, right? When you open up something like this, right? So there is like a more than 1,000 data record. Yes. How do you prepare the data? So this is a digitizing, right? So that one, let's say. So basically, each data entry you have to entry yourself, right? So that is actually tedious part. That will take several months to build up this data set, right? So you have a article title. You can just record as many information as you want. Depends on maybe some information useful, some not. But really, most important information is the sample size of the study, and also in this one, CC is a cover crop, so this is the treatment, and this NCC is a control, and all the numbers here are the yield. So this is the yield information. So each show that is one study, right? So that's some maybe from same study has several entry, means they could have several treatment, like for example, some add fertilizer, some didn't add fertilizer. For that, we'll treat them as a separate entry. So, but in general, if they only have a cover crop treatment and the non-cover crop treatment, one study should have only one row. Manually. So that's why meta-analysis, as powerful as it is, it takes time. It still takes time. For this paper, we spent probably 2 years. This. So that is from the paper, right? The latitude and the longitude. Is that your question? So Yeah, all the information we get from here is from the paper itself. If they report longitude, latitude, we put it here. If they don't, it's empty, right? So because it's not like essential information, we have to need them. We really the only 3 columns we need is the sample size, the yield for cover crowd, and yield for non-cover crowd. All other information would be supplementary information. In a way, for example, whether they use herbicide or not, whether the soil texture is clay or whatever, and is a dry condition or is a wet condition, what's their annual rainfall. So this is important only later when we try to group them into different groups. I will look at maybe dryland altogether. I will see how many I know is the dryland information. I make a subset of them and analyze them. And maybe I will look at how fertilizer impact this. I would look how much fertilizer they have in each column. But not every study has them. So a lot of other things will be subset of the whole study. So for this exercise purpose, let's basically try to copy out these 3 columns. Sample size, this one and this one, and copy them out. Maybe put into a new Excel data sheet. And the reason, yes, because somehow if you read directly from this file, there are error message. So let's just copy out them to a new file, like this. I think that's what I did in the morning. So so I just copy out the 3 columns, one sample size, and then the treatment. I add one column called 1, because in MetaWin software, you have to have a standard deviation to be able to run the software. But because most of the study don't report that, we just give them the same number, really just the same weight. It doesn't change the results. You just kind of, but then you can run the software. If you don't have that, you can't run the software. So just copy the 3, this 3 column. I just copy out this 3 column and then add a column all like 1, right? Make sure, yeah, you do that. And then after that, I basically have a test file. And then I have to save this as a CSV file. Otherwise, MetaWin won't read it, right? So make sure you try this. And then after this, I can input the data using the text file, right? I can load the data. My screen actually is dead, so but I can see it here. So this one I think is separated by commas. So then you can. So that one you load the data into MetaWin, right? Then you can calculate effect size and also calculate the bar, the confidence interval. So I will wait until you get this part. So remember, right now we have a 4 column. This column is the sample size, right? So basically, that is the information you get from the paper, individual paper. So these 2 are the crop yield. So this is the control. This is the treatment. Or maybe I forgot which is which. Let's say. Yeah, this one is the treatment. This one is control. So column 2, this one is treatment. This one is control. And then this one, we just put the same number. Doesn't matter 1 or 2 or 3. We just put the same number for all of them. So everybody get here? Okay. So after that, you can then calculate the effect size and the confidence interval. Right? So this one, you can say compute. There is one you can calculate effect size. So this one you have to identify what effect size you try to calculate. Right? For us, is a response ratio. You select response ratio here, not HD. Remember HD, you have to have a standard deviation, which we don't. We just use 1. Right? So then you have to specify where is what's the mean value, standard deviation, and the sample size, and what is the control, what is the treatment, right? Remember, we talk about our control is column 3, our treatment is column 2, right? And then the standard deviation is the last one, 4. And sample size is column 1. So yeah, make sure you check response ratio and then make them correctly. So when you hit OK, you will see there will be output tab right now show up. After, okay. So, did you guys get this? Okay. So after you load the data, what I did is, oh, not this one. You can go to compute. So there is effect size. Or you can use this button. Should be the same. You have to save as a CSV file from Excel and then load the data. Yeah, there is a load button here. Only CSV file. Yeah, if you use an Excel file, it doesn't give you error message. I hear. Okay. We'll continue. Okay. And so yeah, here like I mentioned, you have to make a right choice, right? Response ratio, and then identify them correctly, right? So I already did. I don't do it again. But this is 3, I think. This is 2, and then this is 4. This 1, and then you hit OK. Because I already did, I don't do it again. It should be the output one. You should be able to get this one output. Everybody get this? So for the output, you can say it give you the effect size here until 1000 something. So basically, each data record it will calculate effect size for you. So far, so good. So after this, that's the effect size, right? So that's not the final product. So the final product would be the analysis. So there are more complex version, but let's just use the basic meta-analysis. So that one, you identify what your effect size is, right? For us, it's the response ratio. You just do response ratio, and it's log transformed. So you don't need to change anything, and then OK. And then here, you have to click bootstrap. Bootstrap, statistically, if you have one value, right, they bootstrapping like many times. You can, default is basically 1,000 times, but you can do 10,000 times, like make the number more accurate. And yeah, that's the only thing you do. And you can hit OK. It should be calculate the bootstrap CI, or yeah, there are some corrected ones. Should be very similar. So that will be our final number, this one. So that will be the confidence interval we are talking about. So that will be the response ratio. That's if you convert to regular, it will be like this. So that will be the one you are using to plot. So that will be this one. So you can use any other software. So this one doesn't, the MathWin doesn't plot very well. You can use other software. But the number gave you this mean value, and this is a 95% like a confidence interval, right? So let's see. So that's basically from 2% to 4%, right? So then that's, for each individual record. Sorry. So that is overall results. So should be very similar to the ones reported in the paper. But remember, this is based on bootstrap calculation. That means each time you run this, it won't be exactly the same because it's just a random calculation. So, but the magnitude should be very similar. Maybe a small change in numbers, but should be very, very similar. So for this particular one, this number should be very similar to this one. You can say that's 2%, that's 4%-ish, right? So that's the range you should look at. So basically what we did so far, we just generate this guy. And if you want to generate others, you can use the same data set. For example, that's the overall results. If you look at legume only, you can go to that data set, just look at legume, and then run that again. You should be able to get this. And if you use like the others, you can try. So I guess maybe I will let you guys yourself try to maybe run legume on your own. Get the data set, load into the software, and try to run it. Hopefully you'll get these results. Then you should be good. So again, that's the difficult part is collecting the data. But after that, you should be able to run this, generate figure like this. So that's the procedure. Any questions? So can you speak louder? Sorry. Okay, sure. So just repeat the procedure again. So you mean like run the software or just talk about the procedure? Okay, software then, right? So again, the first thing is after you download the data, right? So I copy out these 3 columns and I just create a new file, just being simpler. So that's the new file I created. That's a 3 column, and then I add and then I save this as a CSV file, right? Because otherwise you won't do. And after I do that, so this one I have to, let's see whether I can clear all the data. Because the problem is it will be, maybe I will try just load this way. I will just load again and see what happens. So I use commas, so that will be separated better. And then, okay. So so that right now I read in all the data. So after this, you can go to effect size, this one, or under compute there is an effect size, right? So you do that, and then really the important thing is make sure you click response ratio, not HD, and then you identify the column. The mean value is this is the mean value, right? So that's all the column are mean value. So control is 3, treatment is 2, and the standard deviation, that's the one we create like the 1, right? So that's the standard deviation, and then sample size is 1. So just make sure you identify them correctly, and then you hit OK. Should automatically give you this is your data. So you create a new tab. So that one has all the response ratio here. And then after you have this, only after you have this, you can do the meta-analysis, the analysis tab. So you click analysis, right? So we run basic meta-analysis, and then really the only thing we use response ratio. The only thing you need to identify, click is a bootstrap, right? So you can make this bigger number, like it take longer, but the results should be more accurate. So after this, it will give you, so this will be the essential information you want to have, right? You can say the range is actually very similar if you use 1,000 times or 10,000 times, right? So this will be the bar, and the mean value, right? You have that's the mean value 0.03, and then the confidence interval is from 0.2 to 0.4, right? So you get that bar, right? So that will be really all the procedure you've done to be able to get that. And again, if you want to try again, you can look for like only legume, right? Like mentioned, in this data set, we have all the information here, whether they are legume or not, right? You can see there is a cover crop family, right? You can actually look, maybe just select only legume, right? So you should be able to, so all this data are legume, and then, but you can basically still doing the same thing, but only select the legume part, right? So then you run the same analysis, you should be able to get a different bar, right? So that's how do you do it? So again, the data set is already there. We already built that. But if you do your own study, really the time consuming part is really how do you build this data set, right? So that will take time. Uh-huh. What is that and why we need to select that column? So, I mean, for this particular case, we know which column represent for, right? So we know what they represented. So if you have your own data set, you just need to label them, remember it. So, because when I do, this is 1, 2, 3, 4, really, in the software. This is 1, 2, 3, 4. So this is column 1, this is column 2, this is column 3. Yeah. So that is what I am getting. Column 1, column 2, column 3. Yes. After that, since iteration is also column is 4. Why? Why there is a 4? Sir, he is asking about the software that column 1, column 2, exercise calculation. Yeah, no, I know what you mean. Yeah, you are talking about here, right? Hmm? Right. So this is based on. Yeah, so that's based on your data, right? So because here I know, again, I copy this one. This is column 1, column 2, column 3. Remember, right? So that's what they stand for. This is my column 1, column 2, column 3. Column 1 is the sample size. That's why I select when I do sample size. You see? Sample size is column 1. Standard deviation is column 4. Because this one is the one I added. And this one So this is a 3 because the 3 is a treatment. The 3 is a cover crop. Remember, this is a column 3. That's a column 3. Because this is a, oh, sorry, no. Actually, no, this, no, sorry, this is a, no, this should be control. Column 3 should be control. So this column 2 should be treatment, right? Yeah. So I think we did it correctly when we ran it, but here, yeah. So this one 3. This is 2, right? Yeah. So yeah, we ran it correctly, but here. So that makes sense now. So it really doesn't matter which one. It's really based on what you actually put the data. You know which one is the treatment is your column, which one is control is your column. That's just up to you. But for this particular case, because we know which is treatment, which is control. Any other questions? Does this make sense to all of you guys? Right now you know what it is? So remember the column 4 is the one I just created in another file, right? So that's a column 4. It's just yeah, just same number. You put any number there. Because for when you digitize the data from the individual paper, very few will report you the standard deviation. You don't have that information. That's why you give them the same number, same weight. It doesn't change anything. But you have to have that because if you don't have here, if you don't specify standard deviation, if you don't have a number, it won't run. You have to put a number there. But in our case, we just put the same number. Any other? Yeah. Yeah, so really what we do is, for this one, right? So I guess, you can say, for example, if there is a study, like, when you read the method section in the paper, it will tell you, for example, exactly what the keyword we use in Web of Science to actually search all the papers, and then what the criteria we use to filter the papers, and then whatever left over, that's the one we are going to use. So, maybe 100 paper, maybe 200, maybe 50, right? So we have a list of a paper we will use. So, and then after we have that list of a paper, for each individual paper, I will put it out and then just record the information from that paper, whatever they have. Like where's the location, where, what the cover crop species, what the fertilizers they use. Some maybe have this information, some don't. If they don't have it, we just keep it open, keep it blank. You just keep doing for all of them. So again, the only important part is really these guys. What's the sample size they did, and then what's the yield they produce. That's the most important information. And then you just keep recording every paper. And then after you maybe go through 100 paper, you build this data set. So does that answer your question? You're clear about the procedure? So the tricky part is, not every paper report everything, right? There will be a lot of open space here, blank space. Some you can say it's not evenly distributed, right? So some people have this information, cover crop nitrogen rate. Some doesn't. It doesn't matter because later when we do different groups, we only select things. When they report this, we'll put them together. We'll run meta-analysis, and we'll have a confidence interval for that particular thing. If they don't, we just can't report them. So any other questions? Yes. Mm-hmm.
What do you mean by sample size? Sample size. What is it?
So sample size is, for this particular case, that will be, so that's the one they report in the paper. They will say, I have 4 replicates, and that sample size is 4. So they, if they do cover crop impact on yield, they won't just do one field. They will do like maybe 4 plots. So they will say their n equal to 4, and we'll just put n equal to 4. So they will tell us in the paper. We just read that number and put here. So how many replicates essentially? How many replicates they use? Yeah, some people use 3, sometimes use 4. That's a very common, either 3 or 4, right? Because only 3 you have a standard deviation, right? Any other questions? Wait. Areas. Oh, you mean like where? How do you apply this method to what kind of area? So, essentially it could be any area, but you have to be able to identify control and treatment. Essentially they have to have some kind of treatment. Yeah, you can do forest, right? Like a lot of people, if you increase CO2 for that forest, right, you want to say how that change hydrology, right? So your treatment will be CO2 enrichment, and then you have a control. And the forest hydrology will be either, stream flow, or could be like soil moisture. You can do any of that. So, and you can do anything. Yeah, it's very broad. So I would say like if you're familiar with the procedure already, you are comfortable, I will encourage you to do that on your own for the legume one. Like if you can compare that with the results from the paper. You know whether you did correctly or not. But if you don't want to do it, that's fine. So yeah, I guess that's pretty much for the tutorial. If you are, yeah. So ECC just means like cover crop treatment here, and NCC is a no cover crop treatment, because yeah, that's our own labeling. It doesn't make sense. I know. For me, yeah, somehow my student use this one. Is you can use whatever makes sense to you, right? I would say I would use T or C, probably make more sense, but because a lot of time people use E because enrichment, like a lot of treatment is enrichment. That's why meta-analysis, a lot of people they use E and C. But there is no requirement, whatever you use, as long as it makes sense to you. So yeah, so right now it's basically up to you, right? So if you are comfortable with the method, you want to try legume part, you can copy out the data and try it. If you don't, you can take a break before the next lecture, which is not by me, fortunately. So I will be around if you have questions. Yeah, I'll be around for another half hour. So there is a question. Hmm? Yeah, I will. It started, right?
Start.
Yeah. All right. Sure. Okay. Oh. All right. Good afternoon, everyone. This is our second tutorial this afternoon. So basically, Dr. Somil and I will work together. We will talk about the flood frequency analysis using R. I heard on Monday you guys already did the one using Excel, right? So, but we know Excel has limitations for large data set. So that's why today, we'll talk about using R language, using probability function to do the flood frequency analysis. Right? So the idea we're talking about for flood, but in fact you can use the same thing for drought, for other disaster as well. Right? So yeah, I guess without further ado, I give to Dr. Somil. He will give you a brief introduction, and then we'll go to the tutorial. Yeah, you put on. Put. You have to be closer like this.
इसको मैं ना लगाऊं इसको something happened.
ये लगा लिया
हाँ लगा दिया
Yeah.
इसको मेरे को कैसे लगाना है ऐसा लगाना
और मोबाइल नहीं आ रहा ये मोबाइल से कनेक्ट करा था बोल के देखो
हेलो
ठीक है अब सही आ रहा है
So in the last tutorial we primarily talked about flood frequency analysis using empirical method, right? What is exactly flood frequency? So what do we mean by frequency analysis? So basically frequency analysis means, let's suppose you have different sets of flood data. Flood data means you can generate the flood data either from the maxima approach, the block maxima approach, or maybe you can do some sort of peak over threshold method, which we have already discussed, है ना, कि how do we apply the peak over threshold method for identification of the maximum flow series. Okay, So suppose you have one particular station in one particular river basin, you can imagine any river basin, and for that particular station you have the flow time series, and then you have applied that block maxima POT, and then you have got some sort of flood data set, the peak flow of a particular site, temporal data for each different year, for example. When we are saying that frequency analysis, which we are saying, we are associating that magnitude with the probability. For example, you have 1000 qmax, 500 qmax, or let's say 1500 or 2000 qmax, or very extreme, the magnitude events. We are trying to associate the magnitude of whatever we have recorded in that particular location with the probability of occurrence. In very simple word, suppose you have 50 years of record of extreme flow time series, and now let's say if some layman person will ask you ki what would be the magnitude of 100-year return period flood, giving you, if you have the record of 50 years data set for one particular station. Why it is important? Because let's suppose you are building some sort of reservoir, you should aware about ki what could be the possibility of the magnitude which can occur in 100 years time period, or let's say 50-year time periods. Let's say you are also planning some sort of smaller structure, so then in that case you are also thinking about, you should have a better understanding about those floods which are occurring very frequently, 10 years, 5 years, like that. That is why this frequency analysis is very important. In the last lecture, we have primarily talked about the frequency analysis estimation using very empirical method. What was that method? Can we recap? So I have given you some sort of time series data. Okay, so this is this is not a lecture, this is a tutorial. So if you just recall that whatever we have already done, that would be little bit easier for building the more complex concept in this tutorial. So yes, so we have done this descending order, ranking of the data. We have done basically rank the data, the highest is the first one and the lowest is the last rank. Then we have done some sort of empirical probability formula. What was that? Capital P is equal to m by n plus 1. So m is here the rank of the data, that value you have, the flood, and n is your total number of values. So based on m by n plus 1 calculation, now you will be able to calculate probability of each different events, right? Now you have calculated the probability of each different events. Now you can reverse that probability values to calculate the time period. T is equal to 1 by P. Now when you have done 1 by P, you will be able to calculate the return period of the flow. So based on this particular calculation, you have also performed some sort of graphical analysis where we have used that time period, that return period value as x-axis, and in the y-axis you have used that transformed or descending order data set, ranked data in your y-axis, and then you made some sort of plot. You have transformed that x-axis into logarithmic scale, and then you are able to calculate what is the formula of your x and y. Y is equal to something x plus something, like that. And then based on this formula, what is the advantage of this formula is you will be able to calculate not beyond that values. For example, you can put 100 year, you will get the flood value. If you put the 50 years, you will still get the flood values. This is a function you have generated where you are using different x values to calculate the magnitude of flood. So you also recall in the last class when we were matching our results with the observed data and the empirically calculated 100-year flood record from that equation. there was some sort of error, है ना? So that was 2800 or something we got, but originally it was something like that, more than 3000 the lower magnitude return period flow was there, which means when we are using some sort of empirical formulas, there is a high chances that you may get some sort of uncertainty, right? It is empirical, so which means there is a scope of opportunity to add more advanced concept in flood frequency analysis, so that we can get more reliable 100-year return period record or 50-year or whatever number we are assigning, we can get that. Achha, when we are saying flood frequency analysis, it is not only restricted to flood only, okay? When we are doing the frequency analysis, it can be also be applied in drought also, because floods or drought or let's say precipitation or anything, any extreme events can be dealt with the frequency analysis formula procedure. Okay, when I am saying we are applying the extreme value theory, in the extreme value theory you recall that there are 3 different types of distributions which are possible. So this is we have already discussed. Okay, so this one. So in the extreme value theory, so this is the little bit more advanced version of the frequency analysis. When I am applying these kind of different types of distributions, it is not only restricted to flood only. If you have, let's say, drought data, how do you get the drought data? What kind of the indicator you will use that will suggest that is the drought? How many types of drought can exist? 4, 3, 5. Mainly 4. Can you name them? Yeah. So for example, if you are talking about the meteorological drought, what kind of the indicator you will use to tell that okay, this is a meteorological drought? Rainfall. Rainfall and temperature. Okay. So when you are using rainfall and temperature, you will get some sort of index that is called standardized precipitation index, SPI, that will tell you about the meteorological drought condition. Okay. So suppose meteorological drought conditions, if it is going beyond a certain threshold, that will tell you about the complex nature or let's say extreme nature of that drought condition in certain region. Okay. What would be the threshold? If it is more negative number, I think that is more drier condition, right? If it is more positive number, that is more wetter conditions we are saying. So if it is more negative numbers, that you can take as a frequency analysis formula, you can still use that similar way, but in the drought conditions you can do reverse ranking. Okay, the lowest number, that is minus, let's say -3, -5 or something like that, that would be the highest order, and then the rest of that, that's the lowest order, like that. So you can use that values to do some sort of drought frequency analysis as well. Now you can also apply this frequency analysis in your hydrological drought conditions. Hydrological drought conditions क्या क्या है? SPEI, standardized precipitation evaporation index, right? When we are adding the evaporation here, that will become your hydrological drought conditions. So similarly, if you add some sort of socio-economic parameters or crop yield or agricultural productivity like that, that will become your agricultural drought. Yeah, if you add, let's say, soil moisture then that will become your agricultural drought. So that is what I'm describing here. When we discussing about flood frequency analysis, it is not only restricted to flood only. You can do this kind of analysis for all these different types of extreme events, which are rarely happen in different different areas or different places like that. So what is the most advanced form of this frequency analysis? It's called extreme value distribution theory. In the extreme value distribution theory, we have talked about there are 3 types of methods which are possible. One is called the Gumbel distribution. So generally these methods are dependent upon 3 variables: shape, scale, and that is alpha, what was that, mu, sigma and eta. So particularly this is location, this is scale, and this is shape. eta parameter is called shape. You can write, you can note down somewhere. Okay. When you are calling eta is equal to 0, shape parameter is 0, which means there is only two parameter, alpha and not so alpha, this is mu and sigma. Then that will become your Gumbel distribution. Okay. When we are talking about eta parameter is greater than 0, that is called your heavy tail distributions. Heavy tail distributions where we are applying the Fitchett distributions, where eta parameter is 0 greater than 0. That is basically a function of three different parameters, mu, sigma and eta. When we are talking about the Weibull distributions, then eta is less than 0, should be a negative number, and in that case you have also still have the mu, sigma and eta. There are three different parameters that will define the different size. So if mu eta is equal to 0, that is Gumbel. If eta is greater than 0, that is your Fitchett, and eta is less than 0, that is your Weibull. Okay. Now you will ask question that how do we know that which distribution will fit? How do we define that? So then we have also talked about in the last class that there is a generalized extreme value kind of formulation where all these three shapes are there. We have to so that will adjust the shape parameter based on your data records. So suppose here you can see that these are the three different distribution function. Here if you look at particularly the Fitchett one, here it is heavy tail distributions, which is basically why it is heavy tailed, because we have a higher probability compared to other different distributions like that. When you have higher probability, what do we mean by this? In this particular part, Fitchett, why Fitchett has heavy tailed, or let's say if Fitchett has higher probability values in the most extreme direction, what do we mean by this? How do we interpret? If probability is higher compared to this one, which means if let's say there is a certain magnitude event is here located, which means it has a higher probability of occurrence when we are fitting that distribution to Fitchett. Suppose if there is a data set which is following Gumbel distribution, which means the extreme end conditions will be relatively lower probabilities compared to Fitchett distributions. So when data set is telling that the data is behaving like a more Fitchett distribution, which means the extreme and extreme conditions, we are taking all the extremes here, but within that extreme there is a more extreme conditions would have higher probability in the Fitchett distributions compared to other different types of distribution. So this is the theory behind the more complex way of dealing the frequency analysis using the data set. Now I hope you have already installed our studio, everything is installed. Okay, now we can go to that. Yes, we'll do that, don't worry about it. We also give you the material. Okay. Huh? Huh. So now we, yeah, I have done this. So basically now what you can do, you can open the R program, that R studio, and you can use the data set which we have already used in the last class, the data set. Okay. So something like this you can see in your computer or laptop. Okay. So for example, this is our data set Qmax data which we have already shared, है ना. So what we can do, we can make a new sheet, है ना. In this sheet maybe you can write let's say extreme value distribution EVD, the sheet name EVD. Is it visible? No. How to do view? So here you can make a sheet name, that is EVD. Okay. In this EVD sheet you can just paste your the data set, only your year and Qmax you can take from sheet 1 or sheet 2. So you can just copy these two column, year and Qmax data, and you paste it in your EVD like this. Only we need this data, the year data and the Qmax data. That's it. Okay. So you have done this. Now we can go back to this R. First of all, I have to just zoom in. Is it visible now? Okay. Now we can use, there is a command here. 1 minute. So there is a import option somewhere here in the right. Import. Okay. So you have to take that data which you have already stored in your Excel file to R, so that we can do some sort of processing of the data. So here in the import option you have from Excel. Okay. In the from Excel you can just click from Excel, and then you can browse that sheet where you have done that EVD and you pasted that data set. You can browse, it is in my desktop. Here, so that is the Qmax data set. I am clicking that data and I am entering it here like that. So maybe that data has been already here. So now you have to change the name of the variable which is going to be created. Okay. So here the Qmax data, whatever it is there, you have to just write data, only data, that is the data where you are storing your files, the data which you have stored in the Excel. And here is a sheet is default. So default का मतलब ये होता है कि in that particular sheet this R has selected default sheet. Usually the default sheet is sheet 1. Okay. Now we do not need sheet 1, we need EVD sheet. Okay. So we will scroll down here and then there is a EVD sheet, we will select this. Okay. And then that is okay. Now you can also see the data here, probably in your computer you can see because I have zoomed it, so that is what I am not able to see that. There is a button is import here, you can just click, and now your data set is here in your R programming environment. So you have year data, you have Qmax data. Okay. Now if you have a very large array of the data set, R has the capability, you can store in that here, you can import the file and you can store the data in an particular variable, and where all these different values will be stored there. Now you can, if you wanted to just remove this section, this written part. Sometimes your screen has been completely filled up, so you need to clear this screen. You have to just press Ctrl plus L. If you press Ctrl plus L, it will remove your whatever content is there. Okay, so that is now removed. Okay, now let's say, how do we now first I will do very basic experiment with the data set, so that you can get in how do we use this R in the beginning. So for example, how to call the exact column name, how to call the exact column from the data set. Here we have only year and Qmax. It is possible that you have 1000 column. Okay, so how do we search that column, key which column I am interested in? So suppose I am interested in Qmax. So we have already stored the data in data variable. You just write data and then you press dollar symbol, and then there is two things it is suggesting, either year or Qmax. Okay, if you write Qmax and just press enter, you will get all the values here, which means you are able to access the data set which are stored in the variable with some simple command. Can you do this in your laptop? Is it okay? Now you can calculate the mean of the data. Let's suppose I am interested is what is the mean of the data. You can do in the Excel also. Excel में कैसे करते हैं? We have to just put down the formula and then select the column, and then that will give you the mean. So here you just write mean, and then you write data, dollar symbol, and Qmax. That will give you the value, which is 756.6 Qmax. That is the mean value of your data set. Suppose you are wanted to know the standard deviation, that is STD. How do we do a standard deviation? Okay, you can find max of the data. So you can use max of the data, that is basically data, then have this dollar symbol, and then Qmax, and then that will give you what is the maximum value which are there in your data set. You can also do some sort of minimum value, data again, then Qmax, that is 49, that is the minimum value in your data set. So now you are seeing that you are again calling again data and dollar symbol and whatever. So you can store your whatever values there in that particular column in a new variable. How do we do that? Let's say I am interested in making another variable which is called Qmax, and then you can use this symbol also, you can use equal to symbol also, and then basically you can store your data set, data, dollar, that Qmax, and this print enter. Now you have created another variable which is Qmax, where all the values are stored in that column. जो whatever the values was there in data variable, it is now stored in your Qmax variable. Now you can play with the data, this Qmax variable. You can make plot of the Qmax. So you can just write plot and then Qmax. It is something like this. You can see here, so some sort of a bubble or some sort of a point plot where we have each values are there like this, and you can also add here lines in the plot. For example, if you write lines, if you write here line or lines, then you write Qmax, it will add the line. Okay, so now you have different line data, and you can see that there is some event occurred here which was extremely high value. There are some events here like that. If you look at here, it shows that these events are completely decreasing, and there is suddenly we have one event here and then another event here like that, and it is like this. You can do. Probably you can also plot, I think two variable here. So two variable, which means let's say you wanted to add here year values also, है ना? We have year, right? So we can also add year values. So data, then year, and then maybe you can call data and $qmax, but you have already created small qmax, so you can add qmax here, qmax, and then you can enter. That is, you have now the year value. And now you can also add, I think, lines, probably data and year qmax. Okay, so now you have the qmax, you have year information. Now you are able to create a temporal plot in the R. Are you able to do that? इसको मैं निकाल दूं क्या? हाँ, जा नहीं पा रहा है, तो मैं निकाल देता हूँ. अच्छा नहीं आया क्या? हाँ SD SD होता है ना, हाँ ठीक है. तो SD with your data and then dollar symbol and Qmax, that will give you the standard deviation. So now you are able to get this particular graph, and that will tell you about the fluctuation of your Qmax with different years. Now can you tell me which year you have highest flow, highest flood value? Which year you have highest flood value? So this is I think 70, this is 71, 72, 73, 74, 75 and 76. So in 1976 you had a very big flood value, and then that is basically represented by this graph. Now somebody has just telling me you can calculate standard deviation by just writing SD. Okay, so I forgot, because I usually also do programming in Python, MATLAB and R. So there is a slight difference in syntaxes, so sometimes I get confused. So SD if you write, so you will be able to get the value for standard deviation, that is data and then dollar symbol and then Qmax. So that is your standard deviation, that is 639.517, something like that. So that is you are also able to calculate the standard deviation. You are also able to calculate the mean value from your data. So can you do median? Yeah, you can also do median value based on the data here and Qmax. So that will also give you the median value, mean, median and mode value also you can calculate. Mode if you write data and then basically Qmax. What is this? Numeric. Okay, leave it. So now this is how we can basically do some sort of basic statistics with your data set. You can have one column, let's say you have multiple different columns, you can calculate mean values for all the columns. Let's say if I type mean and only write data, not I'm mentioning any column, I am not mentioning any column here now. So can we do? No. Is it possible to do that? No. ST and data. Error in data from this cannot be deleted. Okay. Okay, so basically you can do one by one this mean value and you can calculate. Now back to the original problem. How do we do that frequency analysis? For the frequency analysis, we need to have a package called Extreme. EXTREM. E. So that is package called. This is EXTREME. So that is the package which we need to install in our R Studio, so that we will be able to do some sort of more robust analysis on extreme value distributions or frequency analysis and all that. So this is a package name. Package का मतलब ये होता है, so that is a package which is dedicated for some sort of commands which are doing some sort of, let's say, frequency analysis. There are packages which are let's say you can do some sort of machine learning application. There are packages which can be more focused on clustering analysis. There are packages which are more focused on, let's say, time series analysis. Packages are more focusing on, let's say, some sort of financial data analysis. Lots of that. So these are the specific set of commands which are stored in one package, and that package we are using it so that we will be able to do some sort of more complex frequency analysis here. So basically now what we will do, we'll first check whether we have extreme command or not. So this is, you can, so there are several ways you can do that. You can go to the package, and here basically you can find extreme. So this is not extreme actually, this is actually, here you have capital R, and then you have S, extremes. So if you look at here, you can see that there is a one library here, extremes, which are present in my computer. Probably it is not there in your computer, right? So how do we install a package? So your computer is connected to internet, okay, Anna? Okay. So now you can write a command, install dot packages, and then you can write the particular package name which you want to install in your R, that is called extreme, EXTREMES. That's it. So you have to write this name and then press enter. So it says that a version of this package for your is already available. So it's downloading in your computer because it is present in my computer. That is why it's throwing some warning. So if you are able to do just let me know when you have already installed your extreme package. It's done? Okay. Now once you have installed this extreme package in your R, now you can go to your package and just type EXTREMES, something like that. If you type there, you will see that your package is there. Can you check? It's there, right? Now basically you have to call that package. So R does not understand कि I have to work with this particular package. So whenever you open R, first thing is, if your program is dedicating some sort of specific libraries or a specific type of packages. So whenever you open your R setup, R Studio, or it is also applicable in Python also. you have to initialize your program. Initialize means you have to call those functions which are specific to that particular program. Okay? So for this purpose we will call the library of extreme package. So how do we do that? Library, and then we will type here ext. So it will give you the suggestion, whatever the directories are there, libraries, packages are there, it will give you the suggestion. You can just select extreme and then press enter. So now if you check here, it has been already ticked. It is ticked mark. The extreme has been already activated. Now you can play with this extreme package. Is it completed to all of you? Okay. Now basically we can do some sort of very simple. So first of all, let's say you have already. So that's a good practice that when you install a particular package or library in your R or Python or somewhere, basically you can click this extreme, and then you can just go through that documentation of the extreme, because then you are able to learn that how many different types of commands are stored in that particular package. What is the potential of that particular package? So if you look at this documentation page, are you able to access this documentation page? Are you able to access this documentation page? So with this documentation page, you will be able to see that there are several commands here. For example, there is a extreme command here, then you have base factor, block maxima kind of thing, and then you can also have some sort of POT, peak over threshold, then you have some sort of European climate assessment and data set that is there also. You can directly use this data for some sort of model testing and all. Then you have some sort of commands which can calculate confidence interval and all. Then you have a hurricane data set. You just scroll down a little bit more in F section, then you can see that here there is a command called fit an extreme value distribution to the data. So fit an extreme value to the distribution to the data, which means you are interested in fitting a one extreme value distribution with your data set. What is that extreme value distribution? Generally it will fit a generalized extreme value function where all three version of your extreme value distribution will be there. Okay, it will adjust the a different type of your distribution based on your data distribution. So if you just click this command fevd, you will see that this is total description which is given here for to use this particular command as well. For example, here this function has GEV, general Pareto, Gumbel, exponential, and different types of distribution functions. You can also see there are lots of different commands how to use it, and then there is a clear explanation of all the variables which are used to call when we are using that particular type of function. Okay. Now you can go through this later on. So basically this is the command. Now we can go to the plot. Now we want to fit the GEV distribution function with our data. Whatever data we have, we would like to fit that GEV distributions. So how do we do that? So basically first, let's say we can start some sort of fitting of the data. So can minimize this little bit, and then we can do some sort of let's say I am creating a variable called GEV fit. Okay, and in the R, if it is writing like this, it is also say is equal to. You can write equal to also, you can write this type of mark also, that is also equally think that is also equal to sign. Then basically we can write this command fevd, because you have already activated that library. So if you do not activate that library and if you write fevd command, the R will tell you that there is no FEVD exist in the library, है ना, because you have not called that library, that is why R gives you that types of message. But here we have already activated that this package, then we will not expect that particular error. So FEVD, because it is already showing some sort of suggestions कि FEVD में क्या क्या होता है, हमें कैसे लिखना चाहिए, because it has been already activated. Now we can write the data set. तो data set क्या है? So data, and in the data what is where we have to fit the GB model, ईयर में फिट करना होता है क्यूमैक्स में, क्यूमैक्स में ना. सो इफ यू राइट क्यूमैक्स, दैट इज द डेटा वी हैव जस्ट गिवन इट टू दैट FEVD कमांड. ओके, नाउ बेसिकली वी कैन राइट हियर टाइप, हमें किस टाइप का डिस्ट्रीब्यूशन चाहिए, कौन सा डिस्ट्रीब्यूशन हमें फिट करना है. सो हियर यू राइट इक्वल टू एंड देन यू जस्ट से आई जस्ट वांट GEV, generalized extreme value distributions, where we have type 1, type 2 and type 3 kind of distributions which are there, and then basically we will write. अच्छा, एक और बहुत important बात I just forgot to mention during the slide, whenever we are using some sort of distribution function with the data. distribution function हम क्यों कहते हैं, function क्या होता है? So linear regression function or let's say quadratic function. What is this function, or what is the distribution function? How do we define these functions? So basically when we are saying some equation as a function, it is possible that in that particular equation we have multiple parameters. For example, in the case of GEV, there is a mu, there is a sigma, and that is eta. Mu क्या होता है? Location, where that particular distribution is located. Sigma is called scale, what is the spread of your distribution, and eta is basically what is the shape of your distribution, how that distribution is behaving, whether it is heavy tailed or lighter tailed or moderate tailed, whatever, है ना. So this is shape. So when you are calling this mu, sigma and eta, it is possible that there is a n number of combination of mu, sigma and eta is possible. Suppose I give you a data, let's say you have 50 years flood records. How you are sure about कि इसमें जो ये डेटा सेट हमने दिया है, ये डेटा में म्यू और सिग्मा और ईटा की वैल्यू क्या होगी? When I am saying fitting of a distribution to the data set or a function, distribution function, so we are basically essentially suggesting that or referring to exact value of mu, sigma and eta. How do we find that exact value? In the last example जो हमने किया था वो Excel में, you remember we have fitted a line. Line fit किया था ना? Line कैसे fit करते हैं? लाइन जब फिट करते हैं ना, किसी चीज़ को तो मिनिमाइज कर रहे होते हैं ना, हम ऑप्टिमाइज कर रहे होते हैं ना. क्या चीज़ हम ऑप्टिमाइज करते हैं? हाँ, जो टोटल जो है डिस्टेंस का जो हम सम करेंगे ना, सम ऑफ स्क्वायर ऑफ द डिस्टेंस, दैट शुड बी मिनिमम. सो दैट इज व्हाट वी आर ट्राइंग टू मिनिमाइज दैट. देयरफॉर वी गॉट द बेस्ट फिट लाइन. और बेस्ट फिट लाइन जब हमें मिल जाती है तो क्या मुझे पता चल जाता है? पैरामीटर. जो लाइन होती है ना, लाइन तो y इक्वल टू mx प्लस सी होती है. m तो कुछ भी हो सकता है, c कुछ भी हो सकता है, तो कुछ भी थोड़ा नहीं लेना है हमें. m हैज़ टू बी अ स्पेसिफिक नंबर, c हैज़ टू बी अ स्पेसिफिक नंबर दैट विल that follow that condition that the sum of the square of the distance has been minimized already. You got this concept or not? जो मैं समझाने की कोशिश कर रहा हूँ, इसे कहते हैं पैरामीटर एस्टिमेशन. पैरामीटर एस्टिमेशन ऑफ अ फंक्शन, ऑफ अ डिस्ट्रीब्यूशन. उसका मतलब ये होता है हमें उन पैरामीटर्स को फाइंड करना जिससे हमारा जो पूरा फंक्शन है या हम जो कुछ फिट कर रहे हैं, दैट हैज़ टू बी मिनिमाइज्ड, दैट हैज़ टू बी ऑप्टिमाइज्ड. कि उसके बाद उसकी जो वैल्यूज़ हम उसको कैलकुलेट करेंगे, दैट शुड नॉट बी अंडर वैल्यू और ओवर वैल्यूज और हाई वैल्यूज लाइक दैट. इट हैज़ टू बी अ वेरी minimum error should be there. So that is called the parameter estimation. अब parameter estimations के बहुत सारे method होते हैं, तो मैं ये बोल रहा हूँ ना, you can write down, and if you have any further questions about this you can contact me, or you can also read this through internet as well, that will help you a lot. तो पैरामीटर जो एस्टिमेशंस के मेथड है, अभी तो मैं डायरेक्टली लिख दूंगा MLE, मैक्सिमम लाइकलीहुड एस्टिमेशन मेथड. तो मैक्सिमम लाइकलीहुड एक वन टाइप ऑफ मेथड है जो बहुत ही वाइडली यूज होता है. MLE एक प्रोसीजर होता है जिसकी मदद से हम पैरामीटर को एस्टिमेट करते हैं, और जब हमारे पास एग्जैक्ट पैरामीटर आ जाते हैं, कौन से पैरामीटर, म्यू, सिग्मा एंड ईटा, उसके बाद हमें पता लग जाता है कि ये स्पेसिफिक टाइप ऑफ डिस्ट्रीब्यूशन हमारे डेटा को फिट करेगा. ठीक है, तो ये है पूरी कहानी जो आई वांटेड टू जस्ट एक्सप्लेन हियर. सो हाँ, M and C इज योर पैरामीटर एंड X इज योर वेरिएबल. पैरामीटर और वेरिएबल में अंतर समझते हो क्या होता है? Yes, should be constant. Yes. So basically, so now we are fitting a extreme value distribution in our data set with FEVD function. We have already called that Qmax data from your Excel sheet. Data this dollar sign Qmax and then type, and then we will write here what is the method of parameter estimation. So we will write method is equal to that is, let's say, MLE. There are other methods also present in the module, you can go through that as well. So we will just use MLE to get the parameter, okay, and then we will enter. Now your data has been already fitted by one sort of that extreme value distribution. ठीक है, अब now you, so that is already stored in GEV fit. जो वेरिएबल हमने बनाया ना GEV fit में, this variable has already stored all the information, necessary information which is there, which is already fitted in your given data set. Now I am interested to look at कि ये है क्या, how it will in the number form can we see. So if you just write, let's say, GEV fit, are we able to get something? Yeah. So here probably if I just make it like this, so here if you look at what kind of the parameter estimation method we have used, maximum likelihood estimator, ठीक है, MLE, और इसमें ये सब चीज़ें तो इसके इंटरनल फंक्शंस हैं. नाउ वी आर लुकिंग एट एस्टिमेटेड पैरामीटर्स. ठीक है, अब एस्टिमेटेड पैरामीटर लोकेशन क्या होता है, म्यू, लोकेशन म्यू होता है. म्यू मतलब कहाँ पर वो पर्टिकुलर डिस्ट्रीब्यूशन लोकेटेड है. स्केल मतलब उसका जो स्प्रेड होता है, दैट इज स्टैंडर्ड डेविएशन, दैट इज 332.92, ओके, एंड शेप इज 0.417. अब 0.417 का मतलब क्या होता है, if shape is greater than 0, which means we are fitting a GEV distribution here, okay. In the GEV you have type 1, type 2, type 3. ठीक, type 1 क्या है, गंबल, जहाँ पर ईटा की वैल्यू क्या होती है, 0 होती है. टाइप 2 क्या है, फ्रिचिट, जहाँ पर ईटा की वैल्यू क्या होती है, ग्रेटर देन 0 होती है. और टाइप 3 क्या है, गंबल, वीबल. so where eta की वैल्यू क्या है, less than 0, okay. Here what we have got, so this is eta की वैल्यू is greater than 0. eta मतलब shape, eta is shape, mu is your location and sigma is your scale, eta is your shape. So eta is basically greater than 0. Which distribution it is fitted in your data, Fritchett, right? Although we have fitted the GEV, but within the GEV the specific form of the distribution is Fritchett. Fritchett का क्या जो है वो होता है कि it is heavy tail distribution. Heavy tail distribution मतलब इसमें जो extreme events की probability of occurrences है, that is quite high compared to other distributions like that. So that is the basics of. Now you have some sort of different parameter AIC and BIC. AIC और BIC का इस्तेमाल हम तब करते हैं we use that AIC and BIC these values when we are selecting 2 or 3 or 4 or 5 different types of distributions. Suppose let's say you have already fitted Fritchett, Weibull, Gumbel and some sort of log distributions like that. So you wanted to set कि कौन सा distributions हमारे data को best fit करेगा. In that case you just look at AIC or BIC value. Whichever has the lowest value, you just select that distribution. Suppose you have 4 different fitted distribution in your data, and all these 4 different distributions will give you different AIC or BIC values. Whichever has the lowest, you will just select that distributions for your data that is best representing your data set. ठीक है? So ये है मतलब now we are able to calculate the location, now we are able to calculate the scale, now we are able to calculate the shape and with their error also. ठीक है? Error मतलब पैरामीटर जब हम estimate करते हैं तो there are errors, uncertainty will also be there, that is also be calculated by that function. Okay, so that is basically 416 plus minus 59 point something like that, that is error. 332.92 is scale, plus minus is 55.78 and this 0.41 plus minus 0.017 like that, that is your uncertainty. Now this is a summary of your GEV fit. You can also use this summary command, and I think you can use this FE, no, what is that, GEV fit. That will I think also give you the same thing. Okay, so when you just write summary or just you write GEV fit, you will get same information. Okay, so this is a summary of your fitted distribution with your data set. Now let's say अब हमारा दूसरा काम ये होता है, in the second way you wanted to just explore how this graphical representing your data. अब graphical plot वगैरह हम देखते हैं ना, probability distribution plot fit है, फिर empirical है, then theoretical है. How do we do that? So that's a very simple way. So you have to just write here plot command, and then basically you write GEV fit. So that GEV function, that variable you have created na, using the FEVD command, you just write that GEV fit and that plot, and just you press enter. Actually में ये error इसलिए आ रहा है क्योंकि मैंने इसको minimize कर दिया था probably. हाँ. So basically let me do some sort of zoom out, zoom in, control minus. Okay, so now you are able to see that the thing here. Okay, so this is your so this is your the graphical representation of your fitted plot. Huh? So this is your the first graph. If you look at, so you have to just write plot command with your fit GEV fit that value variable, and then you have to just press enter. That will give you this particular graph. So if you look at here, this is model quantiles and this is empirical quantiles. इसका ये जो plot है ना, ये वाला, इसको बोलते हैं quantile plot, QQ plot. Quantile मतलब हम we have data set, we can do different quantiles, we can calculate in equal spaced distance. That quantiles you can calculate from your empirical data, and that quantiles can be also be calculated from your fitted distributions data. So जो तुम्हारा, so let's say if you have the data that is called empirical quantile, so whatever quantile is coming from the data, it is called empirical, and whatever the quantiles are coming from the fitted distribution, that is called model or theoretical quantile. तो quantile जो हम करते हैं ना, ये इसकी जो बीच वाली लाइन है, that is called 1:1 line. So ideally we assume that your data should, the points should be falling in that particular 1:1 line. If it is falling at that particular line, which means your plot is exactly correct. And you can also see there are some values which are a little bit away from that graph, which means there are needs some sort of sorting or some sort of more better fit of the data set as well. So now you can also look at this particular graph. Here you can see that this is your I guess the empirical data, and this is your so this is your basically the black one is your empirical data, and the blue one is your the fitted that Campbell distribution. This is your empirical quantile and model quantile is similar to this particular graph, and this particular graph is your written period estimation. So here you can see that this is written level and this is called written period. Now you can see that this is you are able to see the different written periods you can calculate from this fitted GEV distributions. So here you can see there are different written period values 2, 5, 20, 100 and 500. 500 is too much with your let's say 50 years time data. Generally we prefer to use double of the written period. अगर हमारे पास 50 साल का डेटा है ना, so we should restrict ourselves to just calculate 100 year, not more than that. If you are calculating more than that, you may end up getting more uncertainty in your estimates. So basically you will have this 100-year record like that. So I think this is you have 46 or 47 years data, so you can go up to 100 year, and that you can calculate from this particular fitted results. So this is basically the graphical representation of the data set. So you can use any data you have, so it's not restricted to your flood only. Let's say you have temperature extremes for different year. You can just calculate for one particular point what is Tmax value, maximum value in particular year, or let's say you do some sort of block maxima approach and then you make some sort of time series of 100 year of Tmax. You can fit your extreme value and you can get the distribution, and you can also calculate what is the written period of 50 years, 100 years, whatever, है ना. And you can also do some sort of rainfall analysis as well. Rainfall में भी हम कर सकते हैं Rmax निकाल के. You can also do SPEI like that. So for this kind of analysis you can also do. Now this is basically we have done this for this. So now more specifically, let's say if we wanted to calculate the written period of your distributions from the distributions. So suppose we are interested in, so इस ग्राफ में हमें दिख तो रहा है, now we can see that कि 100 में इतना होगा, और we do not know exactly the specific number. How do we get the specific number of your written period? So maybe we can make a variable called, let's say, written period RP, and then basically here you can write some values. Some values basically when you are adding, let's say you, so here you are combining together multiple values. So I am putting here C, then basically 25, 50 and then 100. So that is RP written period. So I am creating another variable, that is RP. I am now interested in to find out what is the exact value of written period which is at 10 year, then 25 year, then 50 year and then 100 year. Okay? So this is variable I have created. Now with this variable I can calculate what is the written level of that GEV fit data whatever we have done. So we can just make written level. So जो magnitude हम calculate करते हैं ना किसी written period से, that is called written level. Written level हम calculate करेंगे with this command, written dot level, within this bracket GEV fit we have done, and then we will add here written dot period is equal to RP. So now if you press RL, you will get these exact values. So you will get 10 year 1659, we have 25 year, that is 2651, 50 year is 3686 and 100 year like 5006 something like that. So this is how basically we got this value from the fitted GeV distributions from our data. You recall that we have calculated something very smaller from your empirical data. Now this is a very different from your empirical data set. That is why we need to have some sort of complex analysis of the frequency analysis using some sort of better representing distribution function, so that we can get exactly what could be the value of your written values or written level for different written periods. So this is how basically we can able to calculate the written levels here. So you can also do some sort of very different analysis. So for example, you can not restrict yourself to fit only GeV. You can use Gumbel distributions also. So let's say I am saying GMB fit, okay, and then here FEVD, and then basically I am saying data and dollar sign. This is Qmax, this is type, let's say that is I am saying Gumbel, GUMBEL, and then basically the method. If you do not mention method, it will automatically take MLE. So there are MLE, there are GMLE, there is Bayesian, there is so many different methods are there. So if you do not write here method, it will automatically take the default one. So if I just type Gumbel, now it will fit Gumbel distribution. Okay. If you now plot the Gumbel distribution, it is something like this. Okay, it looks like it is better representing, probably not. So basically we can check whether the GeV or Gumbel is which is giving you the best result. Now you can basically go to the log. So there is a way we can basically compare 2 or 3 distribution together. Some is basically we can go to the summary, and then we can use GMB fit, and then basically you get some AIC value and BIC value. That is AIC is 695.16 something like that. Then you can go to again summary, and here we have done GEV fit, that is 689 point something, which means that this is the lowest, so lower comparatively, which means GEV is the better fit compared to your the Gumbel distributions based on this AIC data record. Now this is clear to everyone. Are you able to do this analysis if I give you any other data? You will be able to do that. How do we do that? Can you recap how we have started with? First we have Excel. Using, if you have Excel, you have sheet data, you have to load the data in your R. You have to mention that what could be your variable of the data. Now your data has been stored in the variable. Now you can one by one you can call that column from your data. Suppose in this example you have only one values, one column. Suppose there is a Narmada or Ganga or Kaveri or Godavari. Let's say we have 50 or 100 stations. Okay? In let's say 50 stations, you have data set from 1980 to 2020, 40 years data. Now you can do the annual maximum analysis. You can calculate what is the maximum value for each different year. Okay? How many values you will get? Number of. So if you have 40 years data and you are applying annual maximum approach, how many data sets you will generate? 40 or less than 40? 40 ना पक्का. And when you are applying POT, when we are applying POT, peak over threshold, so there is a threshold and it is possible that you may get one peak or two peak or zero peak in one given year. So is it always equal to the number of years, or probably can be less than number of, can be higher than also. Maybe you can have a double peak every year if you just take lower threshold. It is also possible. It is also possible, that is by some you will get the number of years and number of peaks are equal. Doesn't matter कि किसी साल में 2 पीक आ गए और किसी साल में 0 हो गया तो भी इक्वल हो जाएगा. ठीक है, तो इसका मतलब ये है when you are using the annual maximum series you will always get the values equal to your number of years. When you are using the peak over threshold method, it is basically can be lesser than or higher than or equal to, anything can be possible, है ना. So now you have let's say 50 stations in Godavari or whatever basin, and then let's say you data set from 1980s to 2020, 40 years data or 41 years data. You can calculate 41 peaks using the AMS approach, annual maximum series. So you will get 41 different values for different data set. So you can create an array matrix. First column would be your year 1980, 1981, 82, 83, 84 till your 2020. Second column is your first station. Third column is your second station. Fourth is like that. Then 51 column is your 50th station. This is how basically you can store the data in one Excel file. Okay. Now you know that GEV has 3 different forms: type 1, type 2, type 3. Okay. So now you can add here. So I have done just for only one station. You can make this is as a for loop. Loop में हम कर सकते हैं. You can make this in a loop. Loop समझते हैं आप? Loop, you know loop, for loop. You know for loop? No. If statement, while loop, no. For loop is basically, I'm just giving a very basic thing. For loop is, suppose you are doing one particular task repeatedly. ठीक है? Similar task. Suppose you have 50 stations, 50 annual maximum series, and for 50 stations you are fitting extreme value distributions one by one like that. So this is a repeated exercise. अब इसको हम 50 बार अपने मन से कर लें तो अपने 50 बार तो हो जाएगा. Let's say if you have 1000 value, तब तो 2 हफ्ते चले गए फिर तो. So this is not the efficient way of dealing this exercise manually. So what we usually do, we basically do this analysis in loop wise. So we just automate whole thing in such a way that computer will take care of doing this automation one by one. एक को फिट करेगा, वो वैल्यू को एक किसी वेरिएबल बनाएगा और उसमें स्टोर कर देगा. फिर जब वो काम खत्म हो जाएगा फिर वो दूसरे वेरिएबल में जाएगा और वो एनालिसिस करेगा, फिर वो वेरिएबल में स्टोर कर देगा. समथिंग लाइक दिस. इट्स कॉल्ड लूप. So where we have automating the whole exercise in loop wise, and we have generated the result and stored in some variables like that. Once this reach the maximum point, let's say हमने loop में define कर दिया कि maximum value क्या हो सकती है 50 or 51. When it is reached the 51 value, it will stop. ठीक. So this is called a loop. So let's say you have 51 or 50 stations in any river basin. We can apply this analysis. We can do FEVD or that fitting of extreme value distribution. We can get multiple extreme values. कोई पता तो है नहीं कि हर जगह सेम ही होगा. Parameter will change. It is also possible that type will also change. कहीं पर गंबल आ रहा है, कहीं पर फ्रिचिट आ रही है, कहीं पर विबिल आ रहा है, something like that. Okay. So that will change everywhere. Parameter will also change, and you will get at the end. So let's say you are saying in that program कि मुझे केवल 50 years return period चाहिए सारे स्टेशन का. You can calculate from that automation, or maybe you can also calculate 100 years. Let's say you are interested in the parameter value or eta value कि कहाँ पर फ्रिचिट है, कहाँ पर गंबल है, कहाँ पर विबल है. So you can just generate the eta value wherever eta is less than 0, that is your Weibull. Wherever eta is greater than 0, that is your Fitchett. Wherever eta is 0, that is Campbell. So this is how basically you can play with your data set. So because we have done only for one station, you can do this analysis back your institute or here also with multiple set of the data set. ठीक है, एक और चीज़ बड़ी इंपॉर्टेंट रहती है whenever, so whatever we are doing, we are expecting that we will use in some sort of manuscript writing or publications or some sort of thing, and usually we often see that people comment on your result with uncertainty. ठीक है, सबसे पहले वो क्वेश्चन यही उठाते हैं कि जो आपने एस्टिमेट किया है उसकी अनसर्टेनिटी क्या है, उसका रिलायबिलिटी क्या है. सो जो लास्ट एक्सरसाइज हम अभी करेंगे, सो वी विल डू सम सॉर्ट ऑफ अनसर्टेनिटी एस्टिमेशन. तो सपोज लेट्स से हमने बताया कि 100 ईयर फ्लड का जो मैग्नीट्यूड है वो क्या वैल्यू हो सकती है. सो लेट्स से हमने बता दिया 2000. अब ये, हाँ, अब ये होगा कि ये जो 2000 है इसमें कुछ अनसर्टेनिटी भी तो रहेगी ना, 10%, 20%, 50%. इट डिपेंड्स अपॉन योर डेटा. सो हाउ वी कैन डू दैट अनसर्टेनिटी ऑल्सो. तो एक तरीका होता है, वी विल डू दिस, यू जस्ट राइट दैट नेम एंड जस्ट रीड इट आफ्टर दैट क्लास. दैट इज बूटस्ट्रैप मेथड. बूटस्ट्रैप मेथड को ऐसे समझते हैं, सपोज यू हैव लेस नंबर ऑफ डेटा सेट. ठीक है, तो बूटस्ट्रैपिंग से हम उस लेस नंबर ऑफ डेटा सेट को बहुत ज़्यादा बना सकते हैं. उसको 1000 भी बना सकते हैं, उसको 10,000 भी बना सकते हैं, उसको बहुत सारा डेटा हम बना सकते हैं. When you this multiple data set, we can do some sort of multiple iterations, and this particular iterations will give different results, and ultimately you can calculate what is the uncertainty in your final results. इसको सिंपल भाषा में ये समझ सकते हैं कि when you are applying the bootstrapping, you are generally creating more number of samples from your original sample, and then you are using that more number of samples to calculate the uncertainty. So that is, there is a one very simple way of dealing this thing. So we have already calculated the this this is basically, so basically we can create the confidence interval of this GEV. One is basically generally gives you summary plot also. So this is confidence interval. Then we have done the GEV fit. Then we are writing type where we are applying this bootstrapping method and for the parameter. ठीक है. Then we are using the method. What sort of the method we are using? That method is called bootstrap. Then we are using what type of boot type is, we are generally preferring to the percentage wise. So here we are writing the PERC percentage, and then basically we are giving how many samples we have to create, that is 1000. So this is how basically we are giving these details to the bootstrapping method so that we can generate n number of samples from your data set. If you just click enter, it will take some time because we are doing some iteration for 1000 times. So probably it depends upon your RAM size also. तो अगर हमने enter किया है तो फिर this will take some time and it will give you some result. Generally if you recall, when we are doing that summary plot na, so there was some sort of 5%, 95% confidence bound. ठीक है, तो 5%. So now this is done. So basically now you can look at this CE, IE and GEV parameter, this variable, and then you can see that. So this is your location parameter, this is shape, and this is scale, this is shape, and this is basically the estimate, and this is 2.5% and 97.5% bound. You can also calculate 10% because this is a default value. You can just mention it in that command, it will calculate 10% and 90% also. So we have just calculated, you can also calculate 5% and 95% as well. So that is confidence bound. अब यहाँ पर एक चीज़ प्ले करनी होती है. So suppose confidence bound का मतलब क्या होता है कि this is the confidence bound where you have 95% of the data is there. Okay, exceptionals are outside that boundaries. ठीक है। तो जो हम एरर को एस्टिमेट करते हैं वो हम ऐसे करते हैं कि लेट्स से योर लोकेशन वैल्यूज आर वेरिंग फ्रॉम 382.36416 to 530 and this is the distribution, okay, 5% and 95%. So you can just take random values from different locations, random values from your scale and random values from your shape, and you will generate random 100 different types or 1000 different types of generalized extreme value distributions. ये थोड़ा सा डिफिकल्ट हो रहा है समझने में, बट यू कैन राइट डाउन। तो देखो यहाँ पर हमारे पास जो लोकेशन है वो एक वैल्यू नहीं है, इट्स अ रेंज ऑफ वैल्यूज, ठीक है। अब इस रेंज ऑफ वैल्यूज में कोई भी प्रोबेबिलिटी हो सकती है कभी भी, ठीक है। सो विच मीन्स वट एवर वी हैव फिटेड इन द डेटा दैट डिस्ट्रीब्यूशन, it might have also be some sort of uncertainty, that is what we are calculating from here. अब इस अनसर्टेनिटी को लेके जो फिटेड डेटा में उसमें अगर हम प्ले करेंगे ना तो हमें रिटर्न पीरियड की भी अनसर्टेनिटी पता चल जाएगी। अगर हमने बोला 5000 इज समथिंग योर 100-year रिटर्न पीरियड, दैट माइट पॉसिबल दैट इट इज 500 इज योर प्लस माइनस अनसर्टेनिटी, 10% अनसर्टेनिटी, 20% अनसर्टेनिटी. So that is how basically we can play with your confidence bound to calculate the uncertainty from your data set. So generally when we submit a manuscript or a paper or something like that in any particular study area, of course you will use this concept in your research work. So उसमें generally ये तरीका ये important होता है कि हमें ये पता होना चाहिए कि जो भी हम estimate दे रहे हैं किसी को उसमें कितनी percentage की uncertainty हो सकती है, क्योंकि अगर हमें ही नहीं पता है, अगर हमने बता दिया 5000 और उसमें हो गई 60-70% अनसर्टेनिटी, तो हमारे रिजल्ट्स तो रिलायबल नहीं होंगे ना. सो दैट इज़ वाई वी हैव टू बी वेरी श्योर अबाउट व्हाट इज़ द परसेंटेज ऑफ अनसर्टेनिटी इन योर रिजल्ट, सो दैट वी कैन हैव अ प्रिसाइज application or precise estimation of our different types of application from your data set. So this is how basically we can play with this GV type of functions and calculate the uncertainty with return period. ठीक है. एक और हाँ देखो इस लोकेशन है ना, लोकेशन म्यू, लोकेशन इज अ रेंज, यू कैन टेक एनी वैल्यूज इन बिटवीन लोकेशन and your return period value will also change. So let's take 100 combination of this, 100 different distributions, and out of this 100 distribution you have 100 return period. Now you can calculate the mu and sigma, right? Same तो रहेंगे नहीं ना, तो basically we can take mu and sigma and that is your uncertainty or uncertainty. तो सिग्मा बाई रूट स्क्वायर म्यू समथिंग एक फार्मूला होता है स्टैंडर्ड एरर का, उसको कैलकुलेट करके हम निकाल सकते हैं स्टैंडर्ड अनसर्टेनिटी इन दैट पर्टिकुलर सैंपल. हाँ, सिग्मा इज स्केल, या नो दैट इज सिग्मा इज डिफरेंट व्हाट आई एम टॉकिंग अबाउट. सो बेसिकली व्हेन यू हैव अल्फा सॉरी द म्यू दैट इज लोकेशन, सो यू हैव रेंज ऑफ वैल्यूज, ठीक है, एंड यू हैव स्केल रेंज ऑफ वैल्यूज, शेप इज रेंज ऑफ वैल्यूज. So you can make 100 different types of GEV distribution function. ठीक है, अभी तो हमने केवल एक ही बनाया है. You can make 100 different types of GEV function and out of 100 different types of GEV function you have 100 different values of return period. Let's say I'm only focusing on 100-year return period. So you have 100 different return period values. So you can calculate mean of that 100 return period value and sigma of that 100 return period. That will tell you about uncertainty. You can calculate standard error. You can note down this terminology. Standard error जनरली हम यूज़ करते हैं अनसर्टेनिटी कैलकुलेट करने के लिए. एक लास्ट चीज़ जो बहुत इंपॉर्टेंट है, जो मैंने शायद कहीं पर बताई थी, बट यू कैन ऑल्सो टेस्ट विथ, जब भी हम कभी GEV डिस्ट्रीब्यूशंस वट एवर वी आर यूजिंग इन आवर डेटा सेट, वी ऑलवेज चेक दैट योर डेटा शुड बी IID, शुड फॉलो IID रूल. IID रूल मतलब होता है इंडिपेंडेंट एंड आइडेंटिकल डिस्ट्रीब्यूटेड. अब इंडिपेंडेंट और आइडेंटिकल डिस्ट्रीब्यूटेड का मतलब क्या होता है? इंडिपेंडेंट ये मतलब होता है कि जैसे कि कई सारे डिस्ट्रीब्यूशंस हैं ना, सो कई सारी वैल्यूज़ हैं विद इन योर डेटा सेट, ठीक है. सो लेट्स से यू आर अप्लाइंग द एनुअल मैक्सिमम सीरीज. नाउ यू आर श्योर दैट कि जो लास्ट ईयर में फ्लड का पीक आया था वो इस साल के फ्लड के पीक से बहुत ज़्यादा कोरिलेटेड नहीं होगा. There are no processes are still ongoing which can change the last year peak and this year peak also. That is independent events, right? That is not correlated. हाँ, so let's say अगर हम POT apply करते हैं तो we may get some sort of dependent event also, ठीक है? So that is not a independent events, that is dependent events. So when we are using dependent events, that we will violate the rule of GEV fitting, ठीक है? And that is another rule is identically distributed. Identically distributed का मतलब, let's say you have 100-year record or 50-year record and you divide your data into 25-year and 25-year. 25-year, 25-year ने बांट दिया और फिर 25 ईयर का जो डेटा है, जो मैक्सिमम डेटा है या एनुअल मैक्सिमम सीरीज का डेटा है, उस 25 ईयर का जो 25 वैल्यूज़ हैं, अगर हमने उसका म्यू निकाला, सिग्मा निकाला और कुर्टोसिस निकाला, स्क्यूनेस निकाला, और जो नेक्स्ट 25 ईयर का जो डेटा है उसका म्यू, सिग्मा, स्क्यूनेस और कुर्टोसिस निकाला, अगर इन दोनों में बहुत सिग्निफिकेंट डिफरेंस नहीं है तो हम कहेंगे ये आइडेंटिकली डिस्ट्रीब्यूटेड है. मतलब so suppose let's say you have 50 years of data record of annual maximum series. किसी एक स्टेशन पे हमारे पास 50 साल का डेली डिस्चार्ज डेटा है, ठीक? हमने उस पर ब्लॉक मैक्सिमा अप्रोच लगा दी. ब्लॉक मैक्सिमा अप्रोच में हर साल में एक वैल्यू हमें मिल जाएगी, तो उस स्टेशन पे हमारे पास 50 वैल्यू हो गई, ठीक? अब उस स्टेशन की वैल्यूज़ को हमने 25 और 25 भाग में डिवाइड कर दिया, 2 भागों में, ठीक है? फर्स्ट 25 एंड सेकेंड 25. अब फर्स्ट 25 का हमने मीन निकाला, स्टैंडर्ड डेविएशन निकाला, स्क्यूनेस निकाला, कुर्टोसिस निकाला. ये अलग अलग प्रॉपर्टीज़ होते हैं, ठीक है? और सेकेंड 25 का भी हमने सेम काम किया, ठीक है? नाउ वी विल कंपेयर दिस म्यू, सिग्मा, कुर्टोसिस एंड दिस स्क्यूनेस टुगेदर एंड वी विल ट्राई टू फाइंड आउट वेदर देयर इज अ सिग्निफिकेंट डिफरेंस बिटवीन दीज 4 पैरामीटर्स और नॉट. अगर कोई सिग्निफिकेंट डिफरेंस नहीं है, सिग्निफिकेंट डिफरेंस मतलब 4-5% ऊपर नीचे हो सकता है. अगर 20-30% और 50% is different, let's say that is 5 and that is 10, which means there is a significant difference between these parameters, these, है ना? So which means the first 25 years and the next 25 years has the distribution has been significantly changed. So which means this is not identically distributed. It has to be a similar values or similar range of values. If it is not, which means your distribution has been changed. अब distribution change कैसे हो जाते हैं? Distribution change generally because of climate change. Climate is changing. It is quite possible that you may get the peak which are continuously in the trend line. ठीक है? Continuously increasing. Man candle test लगाएंगे, significant test आएगा, P is less than 0.05. So basically that means you have a trend in your data. अब ट्रेंड इन योर डेटा अगर हम पहला 25 और दूसरा 25 निकालेंगे तो ऑफ कोर्स तुम्हारा मीन डिफरेंट हो जाएगा, ठीक है? तो दैट इज व्हाई दैट इज कॉल्ड देयर इज अ नॉन स्टेशनैरिटी कंडीशन. नॉन स्टेशनैरिटी कंडीशन का मतलब ये होता है कि योर डेटा सेट्स स्टैटिस्टिकल प्रॉपर्टीज इज ऑल्सो चेंजिंग विद द टाइम. दैट इज व्हाई यू डू नॉट हैव द आइडेंटिकल डिस्ट्रीब्यूटेड इन योर डेटा सेट. दैट इज कॉल्ड द नॉन स्टेशनरी नॉन स्टेशनरी कंडीशंस. नॉन स्टेशनरी कंडीशंस का मतलब जो तुम्हारा डिस्ट्रीब्यूशन है, इट इज़ नॉट स्टेशनरी, इट इज़ चेंजिंग विद द टाइम. अगर मैंने कहा कि डिस्ट्रीब्यूशन चेंजिंग विद द टाइम, व्हाट डू यू मीन बाय दिस? विच मीन्स द पैरामीटर ऑफ द डिस्ट्रीब्यूशन इज चेंजिंग विद द टाइम. इट इज़ कीप ऑन राइजिंग और कीप ऑन डिक्रीजिंग और सडनली अब्रप्टली इंक्रीजिंग, ठीक है, और अब्रप्टली डिक्रीजिंग. तो ये सारी चीज़ें होती हैं जिसे बोलते हैं नॉन स्टेशनैरिटी इन दिस. तो बेसिकली व्हेन वी आर डीलिंग विद द जीईवी एनालिसिस, स्टेशनैरिटी इज द प्राइमरी और इंडिपेंडेंट टेस्ट इज द प्राइमरी क्राइटेरिया टू फिक्स जीईवी फंक्शन, ठीक है? जीईवी जो हम लगा रहे हैं ना, गम्बल, फ्रिचेट, व्हाटएवर, वी आर अज्यूमिंग दैट आवर डेटा इज स्टेशनरी. तो अगर हमने एक प्लॉट किया था ना जो डेटा वाला, इट डज नॉट लुक एनी ट्रेंड, इट इज जस्ट फ्लक्चुएटिंग. So that's अब डेटा इज स्टेशनरी. अगर डेटा स्टेशनरी नहीं होता है उस केस में हम नॉन स्टेशनरी जीईवी फंक्शन का इस्तेमाल करते हैं, उसे बोलते हैं नॉन स्टेशनरी जीईवी फंक्शन. और ये नॉन स्टेशनरी जीईवी फंक्शन कैसे अप्लाई करते हैं? वी कैन टेक टाइम एज अ कोवेरिएट और यू कैन टेक एनी पर्टिकुलर टाइप ऑफ stressors. It could be ENSO, it could be La Nina, it could be El Nino, or some sort of global temperature, or let's say deforestation, or human modification, or reservoir operation. Can be many things that can be act as a covariate in your data, and that will basically define how these the flood peaks are also changing with your changing condition of different variables. So this is how basically we can deal with the non-stationary conditions. ये एक advanced topic है. Maybe we can talk about in any different workshops as well, so that you can learn about this. If you have any questions, you can ask. So I hope you got some ideas today with हाँ जनरलाइज पैरेटो डिस्ट्रीब्यूशन. हाँ तो देखो, जब हम AMS सीरीज लगा रहे हैं, एनुअल मैक्सिमम सीरीज, तो GEV डिस्ट्रीब्यूशन इस्तेमाल होगा. दैट्स अ फर्स्ट रूल. जब हमने POT डिस्ट्रीब्यूशन लगाया तो वहाँ पर जनरल पैरेटो डिस्ट्रीब्यूशन लगा. सिमिलर होता है, थोड़ा भी उसके चेंजेस होते हैं, बट ऑलमोस्ट वर्क्स वेरी सिमिलरली. दैट इज ऑल्सो एक्सट्रीम वैल्यू डिस्ट्रीब्यूशन. ठीक है. डेटा अगर स्टेशनरी नहीं है तो फिर हम उसमें वी कैन नॉट यूज द स्टेशनरी GEV फंक्शन. जो स्टेशनरी GEV फंक्शन इस्तेमाल कर रहे हैं ना यहाँ पे, वी विल नॉट बी एबल टू यूज इट. वी नीड सम सॉर्ट ऑफ specific treatment of our distribution, that is called non-stationary GEV function. You can write down, there are lots of papers have been published on non-stationary GEV function, और उसकी मदद से you can also, so this package also gives you flexibility to apply non-stationary GEV function with your data set. You can go through this package. This is a wonderful package. I mean, we have used this package for my lots of different manuscripts. So basically this is a very good package, and you will get lots of more information about how to do frequency analysis. So this is, we are using some sort of flood today, but it is not limited to flood only. इसको flood frequency analysis ही मत समझना. This can be, you can do for heat stress, you can do some sort of drought, you can any extremes. If you think about, you can apply this kind of analysis with that particular extremes as well. Depending upon that, should follow the criteria of independent and identically distributed when you are using stationary GEVs. So if you have any questions, you can ask. हाँ. अनसर्टेनिटी निकालने के लिए हाँ हाँ हाँ. तो उसके लिए तुम you have to generate 100 different shape, 100 different scale and 100 different location, scale and shape. So that would be a 3-dimensional matrix you will create. 100 go to 100 multiplied by 100. That's like 10 to power 6 values. So 10 to power 6 values you will generate. चाय वाले गुस्सा रहे हैं लग रहा है. 10 to power 6 values you will get. So 10 to power 6 में हम 10 to power 6 को भी replicate कर सकते हैं there, but you may also get some sort of random search within that. ये थोड़ा सा कॉम्प्लेक्स प्रोसीजर है, मैं उसको तुम्हें बहुत सिंपल वे में समझाया, बट यू कैन जस्ट रीड अबाउट दिस. इफ़ यू हैव एनी फर्दर डाउट यू कैन जस्ट कॉन्टैक्ट मी, आई विल हेल्प यू आउट. ओके. हाँ 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 हाँ. टुमारोज क्लास इज 9:30. हु टोल्ड यू? विकास. ओके. टुमारो CMIP 6 का डेटा सेट का उसको मैं कुछ कंटेंट भेज दूंगा मे बी, और वी कैन थिंक अबाउट डूइंग दिस टुमारो ऑल्सो. प्रियमित्र जी तो कुछ करा रहे हैं, तो प्रॉब्ली ही इज़ टीचिंग आवर शॉर्ट, सो मे इंक्लूड सम CMIP 6. मैं आई विल आस्क हिम टू डू दैट. हाँ 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 that is also ठीक है. Any other questions? Huh? Tomorrow I don't have. You got something? Thank you so much.